working on both fundamental and applied problems in computational fluid dynamics and other areas of computational physics. He has to his credit of publishing more than 85 papers in the various reputed journals out of 300 archived articles and has written 20 plus books, chapter and 10 plus edited books on various technical topics. At present, he is associated with William Palm, Professor of Engineering, Washington University in St. Louis, and holding many prominent positions in the various institutes and public institutions in the position of director. He has a great credit of publishing more than such a great scholar in the various reputed journals out of 300 such a great scholar, great academician, books, chapter and 10 plus edited books on various technical topics. At present, he is associated with William Palm, Professor of Engineering, Washington University in St. Louis, and holding many prominent positions in the various institutes and public institutions in the position of director. He has a great credit of publishing. Such a great scholar, great academician, and researcher is none other than Mr. Ramesh Agrawal. I would like to invite you, sir. Over to you, ma'am.
Okay. Thank you very much, Dr. Kaur, for your introduction. And I'm very pleased to be here to deliver my talk. I just must say that, as Professor Wage indicated, that one of the objectives is to have the online instruction so that a larger number of people can participate. And this conference has indicated already that there are over 500 people who have registered for the conference, and from many, many countries around the globe. And so I think that this conference is first of its kind. And I do want to mention that I have had a long association with many institutions in India, going back to 70s. And over the years, I have come occasionally to many, many institutions all over the country. And under various programs, starting with some of you may not even know about that. There used to be a program under the United Nations, which is called the Top 10 program. And I visited several institutions under the Top 10 program. For example, the CDAC in Pune, and also IISc Bangalore and ISRO and many other institutions. Later on, Professor Vedula, who is going to be also a keynote speaker, I participated in his program, IUCCE, and I visited many institutions under that program. And more recently, I have been coming to India more regularly under the GYAN program. And also I have been a participant in the SUB program. So it has been my pleasure actually to be able to come under various auspices to be a part of the educational system in various disciplines in the various institutions in India. And now, of course, most of my interactions has been, as Dr. Kaur mentioned, in the area of my expertise, and that is computational fluid dynamics, but its applications to aerospace engineering, to problems in energy and environment. Now, as Dr. Wage mentioned, that the new trend is to bring in the new disciplines into the educational system, not only in India, but this is a trend all over the world. And that is to bring in the tools of machine and deep learning, and that is based on the artificial neural networks, and also the tools that are developing in the area of data science and risk analysis using artificial intelligence technology. And they are already showing some impact, particularly in the area of health sciences, where the data is very important in coming to some of the intractable solutions for example, in the area of cancer research. And similarly, there are areas where we have a large amount of data, but how to harness the data to solve the societal problems which have been very difficult so far. And so these new technologies that have been indicated by Dr. Wage, I think is certainly an area that some other people may address in this particular conference. So this conference will go on for 6 days, and you will certainly benefit on various kind of technology transitions that has been mentioned. Now, I must say right at the outset that my presentation is going to be not dealing with any of these topics, but will be mostly focusing on the wind energy. And there also, I will present a large part of it on the recent research of my students. I was not really clear that whether I should make it a very general kind of a talk, or should I make it more of a research-oriented talk. But I have tried to put in all kind of flavors, but it doesn't include, the kind of newer developments. Although some of my work recently has looked into the development of data science. As a matter of fact, this is an old topic, but it has taken now a new flavor, and because we have the ability and the tools and the computers to do the research and make use of this research to advance the technology. So I think I will now start my talk with this kind of a brief introduction. And let me see if I can share my screen and be able to get my talk here. Let's see. Nope. Just please be patient. I'm trying to see whether. So. Okay, are you able to see my screen?
Yes, sir. Yes, sir.
Yes, sir. Yes.
All right. Thank you very much. So when Dean Kantivar, she asked me to give a topic, then I chose this particular topic because I thought this might be of interest. But as I mentioned before, that this topic, the title of this topic is such that it contains a large component of our recent research. And so I will try to make it a little more general as I proceed, so that you get a flavor of what kind of research is involved and what is its application. And of course, the topic is very important in the current environment. And particularly, it addresses that how we move from the fossil fuel energy that is being used all around the world to derive our industrial civilization. And so how do we move from the fossil fuel-based energy of coal and natural gas to wind energy, solar energy, and to some extent to
Excuse me,
biomass
sir.
as well.
Hello.
Yes,
Hello.
yes, yes.
Sir, your screen is visible, but PPT is not visible. So
The PPT is not visible?
yes. It is not
Can you-
opened yet.
Oh, you cannot see it right now?
No.
Okay, because it is on my screen. Let me see what's going on here. All right, let me see. Share screen. Okay. Can you see the PPT?
Yes, sir. Now it is visible.
Okay, let me turn on the slide and to see whether the next slide is visible.
Okay, sir. We'll let you know.
Okay, just 1 second. Okay, next slide is visible?
Yes, it is visible, sir. Now.
All right, okay, very good.
Yes, yes. Okay,
So
thank
as I was mentioning that this is an important topic because you know that just recently in Glasgow last year there was this COP17 conference was held to address the issues that relate to the world climate and its implications to our civilization. And so in that context, it is necessary that there is a transition, and the transition should take place from the current sources of energy, and primarily they are coal and natural gas and petroleum, and all these sources that we use for electricity generation or transportation or industrial use, we all know can result in the significant amount compared to the pre-industrialized civilization of carbon dioxide emissions, along with methane and other particulates. But the carbon dioxide emissions, they reside in the atmosphere for hundreds of years, and so they are much more important in the context of global warming. Now, how do we arrest or mitigate that the carbon dioxide emissions do not increase? So right now, they are of the order of about 450 parts per million into the atmosphere, and they are on the rise. And if this trend continues, we know that by the turn or towards the end of this century, there may be the average surface temperature of the Earth may increase beyond 2.5 degrees centigrade. And of course, the consequences are well publicized in the media and also in the newspapers. And the people in the academia and as well as industry and government, they all know about the consequences. So in that context, I think this particular talk, it may be interesting to that I'm talking about the energy generation from the renewable, and that is the wind energy. So I think that I will emphasize this particular aspect and what is involved in the wind energy and what is the potential of wind energy in the Indian context. Now, India right now is the third largest emitter of the carbon dioxide emissions. The first one is United States, followed by China, and next is India. Of course, in terms of the per capita emissions, India is very, very small because we have a large population. But nevertheless, in terms of the total emissions, they are significant and they have to be addressed. And so one of the ways also is to move towards the solar energy or the solar panels, because our climate is such that this can be addressed much better. But wind turbines or wind energies also has a potential in basically transitioning from the fossil fuel based energy sources to the renewable energy sources. So this is some of the outline of my talk. And so the motivation I have already mentioned. And then I will talk about what kind of wind turbines potential exist. And then talk about some very simple mathematical formulations. And there some of the research aspects come into play. And so as I said, that the talk will also contain some of the research information. And then I will mention about some of the applications that are being used which are not kind of the standard applications, but slightly different kind of applications in terms of generating some special kind of way the wind energy. And I will mention that why they are particularly special in terms of generating the wind energy. And so those topics are relatively research oriented. So if you look at this particular slide, so it turns out that it shows the wind energy potential around the globe. So it is a very busy slide, but I do want to emphasize that all the type of winds, depending upon the wind velocity, they can be classified in terms of 7 categories. So class 1, class 2, and class 7. So you can see that if the wind is class 1, which is shown by a very light blue color, the wind velocity is of the order of 5 meters per second or less. And if you go towards the wind velocity of, say, class 7, it will be about 10 meters per second. And that is shown in dark black color. And of course, there are many other colors that you can see, and you can see that where the wind potential is very high. So I will just focus on the wind potential in the context of India. And you can see here that most of the wind that is available in India, inland and onshore, is a light blue color. And that means that the Indian, the kind of wind that is available to harness into energy is of the order of about 6 to about 7 or 8 meters per second, and which is not a very high wind velocity to have a enormous potential to harness the wind energy. So that is a limitation. In contrast to if you look at certain parts of the North America and also certain other parts of the globe, particularly even certain parts of China and Japan and other places, the wind potential is very high. So as you can see that there are some few red dots where the wind potential is high, and that is the area of Alaska, for example, or in the United States. And there are other parts of the globe that the wind potential is high, but in case of India, it is relatively rather limited. But in case of India, the solar energy potential is much, much higher. And also in terms of the cost, it turns out that with the way the solar panels are now getting cheaper and cheaper over the years, the solar energy has a much higher potential because we are much closer to the equator and there's a lot of sunshine around the year in India. But nevertheless, in the context of my talk, I just want to mention that this chart is fairly interesting in terms of showing the potential of wind energy. But overall, if you look around the world, it turns out that the wind energy potential is quite high. Actually, the potential is of the order of 50 terawatt. The amount of energy that is being consumed all around the world right now is of the order of 30 terawatt. And with the growth of the population by 2050 to about 9.5 billion people, the amount of energy that will be needed will be still less than 50 terawatt. So in principle, if we can harness all the wind energy that is available around the globe, it turns out that we can really meet the needs of by wind alone, the energy needs of the entire population of the world by 2050. But it is not really feasible because of the limitation of the technology and the potential of the wind that we have. If it is a low speed wind, the technology that is needed to extract all the energy, there is a limitation. And there are, of course, the limitations on the physical principle of extracting the wind energy, and that is what is called the Betts law, that in the whatever energy that is available in the wind, if you can extract all of it, you cannot extract more than 59%. So all these limitations are there. But it turns out that in the United States, 6% of the land is suitable for wind energy development, and you can extract 0.5 terawatt of energy. Now, as I told you that in case of India, of course, inside the land area and also offshore, the potential is much, much lower. And so that is about actually 0.1 or even less than that terawatt. So the wind energy potential for India is relatively limited, but I know that there are many institutions, I personally know that they are doing work in the area of wind energy, and that should be done because I think that that is one of the renewable sources of energy that should be harnessed in the mix of various energy sources. So this is another chart which basically shows the potential. And as you can see that North America has a much larger potential in terms of harnessing the wind energy. And if you look at Asia, and which includes China and India as two major countries, and as well as the rest of the Asian countries, the potential is much, much smaller because the wind energy that is available is relatively limited because the class of wind is only class 1 to 3. But there is nevertheless tremendous growth in the worldwide wind energy. And so if you look at this chart that goes up to only 2010, but you see from 1997 to 2010, there's almost exponential growth in wind energy. And so this chart shows that in 2010, there was 160,000 megawatts of wind energy that was installed. But 2020 data from the International Energy Association shows that this has already exceeded 250,000 megawatt, and about $25 billion worldwide have been spent in the installation of wind energy. And this will continue to grow because I think that the installation of the wind turbines, particularly huge turbines of hundreds of meters in diameter, have become much cheaper than what was the case even a decade ago. So I think that the wind energy has a tremendous potential, and from my previous statements, one should not infer that it doesn't have a potential in the Indian context. And I know that several institutions in India are working on wind energy. So now if we can move from fossil fuels to the renewables, and wind energy is one of the renewables, then it turns out that one can save a tremendous amount of, or one can mitigate tremendous amount of CO2. So this one shows some kind of a estimate, and what you can see that an average wind turbine can prevent the emission of about 1,500 tons of CO2 each year. An average wind turbine, we are talking about a horizontal axis wind turbine, which can generate about 700 kilowatt power. And so a single wind turbine with 700 kilowatt of power, and which means that this is the average wind turbine, and many of them actually are now exceeding the megawatt range. And so you can really, this is one clear case of energy transition. Your conference actually has a word transition in it. So the transition from for what kind of technologies that we want to transition to in order to address a variety of global problems. And this is a problem in the area of the transition from fossil fuels to the renewables. But as I said, that one can use the newer technologies, and particularly where there's a large amount of data available to address the problems of, particularly in the healthcare. And so people are working in all these areas. Now, those technologies that were mentioned, like data science, the artificial neural networks, the machine learning and the deep learning can also be applied to any technology, including the wind energy, because we have a large amount of data available about the wind, and which the data, basically the most important data is that how the wind patterns change throughout the year, that is 365 days, and in a given day, 24 hours, and at different locations around the globe. So that amount of data is available from the weather surface. And if we use that amount of data, then maybe we can come up with more interesting and more creative models, and not only the models, but the way to harness the wind energy more effectively using the current technology. Or we may also come with solutions to use the technology maybe more creatively, and I will mention some of those, so that you can harness more amount of energy from the wind once you know the wind conditions. The other important part, which is very important in the context of knowing more data and for a particular location, is that wind energy is intermittent. So intermittent means that it varies as the wind conditions vary on a particular area. And so as a result of that, but we need a continuous power of the energy. So the continuous power of energy means that we should have a storage mechanism to store the wind energy when the wind is blowing. And then when the wind is not blowing, then that stored energy can be used to provide the continuous wind power, continuous power that is needed by, for example, the households or the industry or other usages that we have. Now, wind energy, of course, cannot be used for transportation, because transportation is a mobile form of energy. So whether it's a car or an aeroplane or a ship, the energy is moving with the vehicle. So that has a slightly different kind of solutions that have to be addressed. But in the case of electrical power, the wind energy solutions with the storage can be interesting and useful. So now you can see here in this chart that the cost of wind energy has gone down. So within a matter of about 40 years, it has gone down from 45 cents per kilowatt hour to about 5 cents per kilowatt hour. So it has become competitive with the fossil fuel energy. As a matter of fact, it has become slightly cheaper than the fossil fuel energy in certain part of the world. It depends on whether the wind installations are available in the vicinity of that land area, whether this is offshore wind or this is inland wind energy sources. So I just want to give you a little bit of history of the windmills. Of course, the history of windmills goes back to about 5,000 years. The Persians were one of the first ones that used windmills. And in the 15th to 16th century, the people in Europe, particularly Holland, various type of windmills were used. And still the Holland or Netherlands is considered as a place where the largest number of windmills are installed. So now I'm showing you that there are all kinds of windmills that have been developed over the years. And so there is a museum in the United States in Lubbock, Texas. And I visited a museum, and that has a tremendous amount of information about the history of windmills, and has a collection of books. And if you go on the website, you will find that if you like to, really familiar yourself, not about how the windmill operates, but also what kind of windmills have been developed in the last 500 years, I think you can find an enormous amount of information. And if anybody has a chance, those who live in the United States or other parts of the world have a chance to visit this museum, this is one of its kind in the world. So I've taken some pictures from there and I put in here, and you can see that there's a variety of type of windmills that have been developed, and there's research is going on. For a long time, the research in wind energy was rather limited. People did not pay much attention to it. But I think in last 20 to 30 years, in the academia as well as in industry, people are paying tremendous amount of emphasis on this research on the wind turbines. So basically, there are two types of wind turbines. One is the horizontal axis, and the other one is the vertical axis of wind turbines. Now, horizontal axis wind turbines are the ones that are mostly installed around the world. They are primarily the three-bladed. I will not go into the reason why they are three-bladed, because we do not have that much time. But there is a very good book actually by Manuel and others. And this book, it shows, it is almost a treatise on the kind of wind turbines and why the wind turbines are the way they are. So this is the horizontal axis wind turbine on the left, and there are a wide variety of the vertical axis wind turbines that have been developed. Now there are issues in terms of horizontal axis wind turbine, because you have to have a tower, and then you have a wind turbine, let us say with 3 blades, which is most common. You have to have a large diameter in order to have the wind power, which is of the order of say 1 megawatt. And so these are of the order of about 100 meters in diameter. Of course, they are very expensive, and these towers itself are expensive, but you can really generate a very large amount of wind, assuming that the class of wind is of the order about class 5 or class 7. Then I'm giving these numbers. Of course, if wind class is much lower, then the power generated will be less. Now the vertical axis wind turbine that are shown in the right-hand side, they are relatively much a smaller scale, and the cost is also smaller, but on the other hand, the amount of energy that is generated is also much smaller. So this shows, that how complex a wind turbine is in terms of the hardware. So there are various type of things that are shown here, that the mechanical power that is generated by the blades on the aerodynamic principles, then that power has to be then converted by the generators into electrical power. And then, of course, that can be transmitted to the transmission lines to where it is needed. But there are many issues involved, that you want the wind turbine to have an orientation so that you can harness the maximum power. So there is a yaw mechanism, and of course there has to be control unit. Control unit is an extremely important part, and there is a tremendous amount of research that is going on, because under the icing conditions, that there is a ice, or there is a hail, or there is a snowstorm, then you have to make sure that these blades, don't shear off and they fly away. So there are a lot of issues in terms of this simple machine that has been around for thousands of years. But as I said, that as people are investigating more and more into these machines, it turns out that these areas are quite rich in terms of technology, both in the aerodynamics aspects, in the control aspects, and also in the manufacturing, that what kind of material you have to use for the blades. Now you can consider using the composite materials. So they are very, very rich areas. I think that the amount of technology that is required in wind turbine, I am finding out that it is as rich as, for example, for an aeroplane, or let us say a commercial aeroplane. So this is certainly a very rich area for research. And as I said, that people are looking at in India as well. So there are a number of companies that, which are manufacturing wind turbines, and they are in order of the output or the number of turbines they have sold. Siemens, Vestas, they're very well known, General Electric, Enercon, Nordex, Senvion, Goldwind, and Sinovel Wind. So these are the main companies, and you might have heard of, Siemens and Vestas and GE. They create, or they manufacture very, very large size of horizontal axis wind turbine. So I will now go into a little bit of a technical part after this brief introduction, that why wind energy is important and why you can consider this as a transition mode energy from the fossil fuel to the renewables. So one of the things that is important, and that is why the class of the wind is very important. So the power is very simple expression. So the pi r is square, r is the radius of the turbine, that is the frontal area. And so that is pi r is square is a very simple expression. And then what you have here is rho VQ. And so what you see is that the wind power is proportional to the cubic of the velocity. And we can show that actually some very simple analysis, which I will not go over here. So if you have, the power given in, say, watts, and the air density is known, which is about 1, and then the velocity is in meter per second, and the radius is in meters, then the curve on the left-hand side shows that how much energy is generated watt per meter square. So the important thing to see here is that this red curve, that the power that is generated goes as a cubic power of the velocity. So that is why if you see at the bottom of this curve that if the wind is, say, class 3 or class 4, then the maximum wind velocity is about 6 meters per second. And so this is not really can create a tremendous amount of wind energy. But as the class of the wind increases, say, let us say 10 to 12, then you can see that there is a tremendous amount of increase in the power, because the power is proportional to the velocity cube. Now, in that context, one of my topics that I will be talking about, which is a research topic that I have a patent also, and that is the airborne wind turbines. So airborne wind turbines means that if your wind turbine somehow is tethered or can be put on a drone and at the height of, let us say, 50 meters above the ground, then you can get the wind velocity, which is of the order of 30 to 50 meters per second. So if you can go to that height, then you can see that the wattage of the extraction of the energy will substantially increase. But there are some other issues that are involved in creating such a airborne wind turbine. It's not very simple, but that is one of the research topics that I will address. So now, and there are many ways that you can analyze a wind turbine. And it turns out that, of course, now we have a CFD technology, we have the computer hardware that we can do the full-scale simulations using the available commercial codes. And I'm sure that those of you work in computational fluid dynamics or any part of fluid dynamics and heat transfer, you might have heard of, say, Fluent or ANSYS Fluent. And ANSYS India, they basically market this code. And of course, there are many other codes. And I know that there have been a lot of development and of the commercial software by the Indian companies. And over the years, there has been a lot of research in developing the computational fluid dynamics codes based on the solution of the Reynolds average Navier-Stokes equations, which are the fundamental equations for the turbulent flow in any kind of internal or external flow system, whether it is a turbine or it is a pump or it is a car or it is a aeroplane, you name it. Anywhere there is a flow, you can use these commercial codes. And I'm certain that your institution, wherever you are, you have these codes and you are training the students in the application of these codes. But before these came along, it turns out that a simple theory was developed by a German mathematician and a scientist, Betz, and he used a very simple model that the entire wind turbine, irrespective of the number of blades, can be replaced by a circular disk. And he called it an actuator disk. And then you simply use the conservation of mass and conservation of momentum. And if you use the inviscid theory, then the conservation momentum becomes the Bernoulli equation. Then it turns out that there is a pressure jump across the actuator disk, which is nothing but the wind turbine. And so then you can do the analysis and can show that the power coefficient is given by this expression. So now it looks like a complicated expression, but it's really not. This is the area, frontal area of the wind turbine. That is the area here. That is a circular area pi r square that I showed you in a previous slide. And U1 cube is the frontal velocity or the velocity in the far stream. So this expression I showed you before, but it turns out that if you have an actual wind turbine installed, and you can also analyze the effect of the number of blades, then you have this particular factor coming in. And this factor can be obtained by analyzing and applying the principle of Bernoulli for the conservation of energy and applying the principle of conservation of mass. So it turns out that you can show that from this power, based on this induction factor, which is nothing but a 1 minus U2, which is the velocity ahead of the actuator disk, divided by the free stream velocity U1. Then if you take dP over dA, then you can show that for A is equal to 1/3, that is the maximum possible power that you can harness. And it turns out that gives you the pressure coefficient is 16 over 27, and which is 0.59. So as I had mentioned before, that it turns out that 59% is the maximum power that you can extract from a flowing wind. And this is a physical limitation. You cannot increase that particular number. Now, if you have viscous effects or the turbulence effects, or you have the actual number of blades, it turns out that the rated power is of the order of about 35%. And the rated power means that you are expecting a certain class of wind. But if the class of wind is further down, then it may turn out that you can get only about 20% of the power that is available to you in the flowing wind in far away. So you can see that these are the limitations that one have to work with. And there are ways that you can extract more power. And that is where this new technology ideas you have to put into place. That is there a way to design the wind turbine more effectively so that it can extract more power? And there are many other issues that come into play, because you are not going to have a single turbine in a single place. You are going to have a wind farm where you are going to have a number of wind turbines. So now the second class of wind turbines, which of course are not that much used, but they are certainly also useful in the sense that because the cost is less. So in a localized setting, for example, in a village setting or in a place where you really are not connected with the main transmission lines, then one can have these non-centralized solutions. And so this is one of the turbines. So you have nothing but a blades which are almost in the form of a two sheets, and then these sheets rotate when they encounter the wind. And so it is a very, very simple kind of mechanism and very simple way to design a wind turbine. So it's called a vertical axis because it is moving around the vertical axis. And so there are examples that people have used the vertical axis wind turbines. So there are two of them. The one I showed you before, that was called the Darius turbine, and then there is Savonius turbine. So these are the examples that, for example, this is in Taiwan, and people are using the combination of the Darius turbine, which is the outer one, and the Savonius turbine inside, and both are vertical axis turbine. And what they are doing is basically providing enough power so that it can use to lighten the lights or lamp, which is there in this particular lamp post. And so this is there, that many countries are using this and trying to, use the wind. And this is, you can see the tower is at a reasonably higher elevation so that the wind speed is significant enough. Now, of course, once the wind is not available, then there is no energy coming in. And so it cannot light the bulb, which is the purpose of it. But if you have a storage battery, even a small battery, then you can supply the continuous power that is required in order to light the bulb. And these are some of the mechanisms. These are some physical mechanisms that make the Savonius rotor to rotate, or the Darius rotor to rotate. And of course, this rotation is very necessary in order to have energy or the kinetic energy available. So now again, I'm going to show some of the work of some of my students have done. And this is where I was saying that I will be digressing from the general talk, in terms of some specific kind of research talk, but I will keep it as simple as possible. And so as you saw that in case of the vertical axis turbine, the Betz actuator disk theory was applicable, and it has been known for a long time. It has been applied to helicopters or other rotating machinery, instead of working with individual blades. Is very simple to apply, and you can do back of the envelope calculations to get reasonable answers. Of course, they will not be very accurate answers, but if you have a large amount of data available, or if you have the other kind of information available, one may like to use some other way to analyze that particular data, maybe using the algorithms of artificial neural network and trying to see that what is the potential of a particular site in terms of the overall generation of the energy from the wind. And then also, what kind of storage mechanism can be developed, and so on. So we are at a stage that can be exploited, but I'm just showing you that we can still do a lot of work by simply applying these principles, but people have not applied. So the Betts theory was developed sometimes in 1940s, and then of course it was not used a great deal because, as I said, there was no need to use the wind turbine as much, and there was no pressure to address the issue of the transition from fossil fuels to wind energy. But again, now here I'm showing you a vertical axis turbine. So vertical axis turbine, you have almost, you can approximate it, particularly Savonius rotor, in terms of a circular disc. So now instead of a disc which is facing the flow, was simply a disc which was perpendicular actually to the flow direction. Now you have a circular cylinder. So now it becomes a little more complicated that how do you apply the physical conditions of a actuator disc, which I mentioned before, due to Betts. So this becomes what is called a actuator cylinder. So it turns out that simple fact that we are applying the theory from a hot or a horizontal axis turbine to a vertical axis turbine makes everything very, very complex. And so now you can see that how do we apply the pressure jump condition? That is very critical. If you cannot apply the pressure jump condition, then you don't have a actuator disc theory. So in this particular case, for a vertical axis turbine, I'm calling it to be actuator cylinder theory. And so I will show you that how we can extend what is existing in the literature to develop this actuator cylinder theory. And this work is based on one of my students, his master's thesis a few years ago. So now it turns out that if you use the simple inviscid Euler equation, just like the inviscid theory of Betts, then in this particular case, there is a pressure jump on this cylinder from inside to the outside of the cylinder. And so this pressure jump is the most critical in developing any kind of actuator theory. So for actuator cylinder theory, it turns out that you can solve the Euler equations, and which are inviscid equations. And of course, you have to linearize these equations because nonlinear Euler equations are very difficult to get an exact solution. But it turns out that if you linearize the Euler equations, then you haven't get an exact solutions for the pressure jump across this cylinder. And this is the solution that you have. Of course, this pressure jump, it turns out, varies as a function of theta. And the theta is this particular angle, from the vertical. And the reason it varies as a function of theta is that the wind is facing only this part of the actuator cylinder. And of course, if it is rotating, then the other parts will again come in front of the wind. But the back part is not facing the wind. So as a result of that, the pressure jump across the front part is very different from the back part. So these are some of the basic considerations. But it turns out that once you have this particular expression, which is already available, and you may be surprised that simply derivation of this pressure was a PhD thesis, and that was done in Denmark. And also I want to mention that Denmark is now the leader in terms of the installation and also the manufacturing of the wind turbine as well as the research. And I had the opportunity many, many years ago, maybe more than about 30 years ago, to visit this particular center. And it's amazing that what they are doing in terms of the wind turbines. So now you can see that, but this is still an inviscid theory. So our goal was to apply the Reynolds average Navier-Stokes equation, that is to include the effect of turbulence and see what happens. So if we do that, then it turns out that not only there is a viscous flow outside this actuator cylinder, but also inside the actuator cylinder. The flow becomes quite complex. And of course, you have to generate the mesh and also the boundary condition other tools. And you can discretize this integral, which goes from 0 to 2 pi of this particular delta p theta. Then you can, and VR is the radial velocity. Then of course, you can sum it from number of angles that you take. You can take 1 degree angle or 2 degree angle, depending upon how much will be the computational cost. So now I will quickly go over instead of spending too much time on the simulations, because if you are interested, there are a number of papers and you can contact me and I can provide you if you are interested in it. And also if you are interested in experimental work, I can provide you that information as well. So this is a typical, in case of computational fluid dynamics simulations. Those of you who have seen this, so this is our vertical axis wind turbine or the actuator cylinder. And so this is the computational domain, and the flow is coming from left to right. So the typical boundary condition is we know the wind velocity here, and here we assume that the pressure gradients have become almost uniform. So this is far away in order to make sure that the boundary condition is accurate. And then, of course, around here, the boundary condition is more important, and that is the pressure jump conditions, that the actuator cylinder jump condition, or also it is called the fan boundary condition or reverse fan boundary condition. So here what we are going to do is that we are going to consider a 1 degree difference. So we are going to digitize the cylinder at 1 degree interval. And so that you have about 360 points for 360 degree circumference. And so as I said only that, there are a variety of turbulence models that we have used to basically analyze the effect of turbulence. So now what I'm showing you is that one of the things that those of you who work in CFD, you might be aware of it, that the mesh is very important. So if you have a very, very thin, very coarse mesh, that you do not have too many points to characterize the domain, you can see that there are a lot of points here. And so the way the topology of the mesh and the way you generate the mesh, they are separate topics. But nevertheless, the amount of mesh that you have is very important because the solution is dependent on the number of points that you use. So for example, if you have a circle, you can define the circle by 4 points, then what you are going to really get is a square. You are not going to get a circle. If you define by 8 points, then you will get an octagon. So the idea here is that you want to be as close to the cylinder as possible. So we here take the number of meshes that we study. And so it is important for any kind of numerical simulation. So you can see that if we have a very coarse mesh, the number of elements is very small in the total number of elements for the mesh, then you have to take an interval of 18 degrees. But as you go and refine the mesh, then you can go to about 750,000 for mesh number 9. And then the interval between the successive points on the cylinder becomes only 0.69 degrees. So this plot basically shows that then you can calculate the power coefficient by the expression that I've shown you before. Then it turns out that mesh number about, say, close to 5 or 6 is sufficient to get the right answer. After that, there is no change in the rotor power, which you're interested in. So which means that if you are around here, which is 130,000 cell, that is sufficient to get the right answer. Now, these are very important points, and I'm mentioning you from a research point of view. So as I mentioned here, if mesh number 5 is adequate, but please be aware that these things are very important if you are interested in this subject. Of course, if it is not that you just want to know what this subject is all about, then these details may not be that important. So now what we are doing is that we are doing, instead of doing the inviscid theory, the main contribution is that we have a main viscous theory with turbulence effects. And now we again see that what are the various components so that we can create, we have now enormous amount of data that is generated by the computer. So now we can take that data and basically synthesize the data in the form that we really like to see. And so that is where we can get some kind of a software that can do that for us. All kind of these softwares are available instead of going about the old-fashioned way. So what I'm showing here is the Vx, the x component of velocity with the x position, and that is the center line position in the domain that I showed you in the last slide. And what is the difference in the viscous and inviscid case? You see there's not much difference. So what it is showing you is that this is the pressure, this is the Vx component of periphery x velocity, this is center line x velocity, and this is the periphery velocity angle. So we can do as many details as we want, but what it shows is that the viscous and the inviscid case, there is going to be difference because now we are taking into account the effect of the turbulent flow, but it turns out that the effects are not that much. and they were all done on a mesh number 5. So they are fairly good solutions. So now you can see the other comparisons, and the wake of a wind turbine is very, very important. And particularly if you are trying to create a wind farm, because as I said that you are not going to have one single wind turbine sitting in some place. What you would like to have, whether you have a shoreline, you will have to have the wind turbines one after the other. Or if you have inland, then you will like to space them so that you can get the maximum power with a minimum amount of land used. So they are the two considerations in optimization, that you are trying to get the maximum amount of power with a minimum amount of land used. So in this case, we are again, the wake becomes very important. And as we know, the wake behind the cylinder will change as you go downstream towards the exterior edge of the computational domain. So it turns out that if we compare that with the inviscid case and the viscous case, so then there is a lot more difference in the case of the viscous versus the inviscid wake. So this is a typical wake velocity profile, and you can, if you are interested, you can see that this is x is equal to 1, which is the viscous case, and x is equal to 1 is the bluer one, which is the inviscid case. So this is a typical kind of things that you expect. And now I'm showing you that what is the effect of the number m equal to 1 and m is equal to 5. So if you recall that, you know, in the delta p theta, that is in the pressure jump, there was a factor m. So the m is actually, the theory is valid for any value of m, but you cannot do the computation for any value of m. So you have to pick certain value of m. And again, you have to see that what is the effect of the exponent m in the expression that I showed you on delta p theta. I mean, I can go back to the slide, but I think that, you know, it may just not be that smooth the presentation, but if you can recall, or if you can remember, that in the solution for delta p theta, which basically is the pressure jump across the actuator cylinder, there is an exponent m, and in the solution process, the m has any general value. M can be 1,000 or 10,000, but of course, computationally, you have to have a value of m which is reasonable and where the solution is converged. But the important thing I'm showing you is that if you choose simply the value of m is equal to 1, you can see what the wake is. And if you choose the m is equal to 5, you can see that how much is the spread in the wake. And this wake calculation is extremely critical, particularly if you are going to use this wind farm in a wind farm kind of application. But not only that, you really want to have an accurate calculation of the power generated. And so this generation of the correct value of wake is very, very important to have a confidence in the solution. So m is equal to 5, I'm showing you here. And now I'm showing you the effect of m. So this is the power generated, and this is free stream velocity. Of course, we know that the free stream velocity goes, with the free stream velocity, the power generated goes in terms of Q. But what is the effect of the m in terms of the pressure jump across the actuator cylinder? It basically shows that for various values of m, from m equal to 1 to 10, there is a tremendous effect on the power generated. For m equal to 10, for the same free stream velocity, the power generated is close to 500 watt per unit length of the cylinder. So you have to have a correct value of m. So it turns out that m is equal to about close to 10 is a good number. So you can see here that after 10 and 15 and 20, the value doesn't change for the power. And so this is power per unit length of the cylinder, okay? And so m is equal to 10 is the right number. So you have to do all these calculations in order to be confident about that your model is working or not. So again, I'm showing you here the effect of m equal to 1 and m equal to 1 and m equal to 20. But as I mentioned in the previous slide, that m is equal to 10 is enough. But then we wanted to go just to see what really happens. But you can clearly see that the flow field completely changes. So the pressure around the cylinder changes as you go from m equal to 1 to m equal to 20. So the model that I am representing you you have to go and make sure that you are applying the model correctly. So it is true in any kind of physical application of any problem, that whatever problem you are solving, it becomes extremely important that you know that what are the assumptions in that problem, and those assumptions that you are using, whether it is in whatever process or mathematical formulation that you have, those assumptions are capturing the actual physics of the problem. And so in your teaching, because most of you are faculty and most of you are in teaching, and I am a teacher as well, although I worked in the industry for a long time, I can tell you that these things are very important to emphasize to the students, that most of the time, mathematical principles are based on some assumptions. For example, the flow is incompressible, flow is compressible, flow is irrotational, flow is rotational, etc. So all these things, what is the consequence on the mathematical formulation? And the final proof is that once you have solution to that mathematical formulation, whether by the computer or by some other means, that solution must be exhibiting or must be close to the reality. So from a teaching point of view, this particular aspect must be drilled into the students, that this is very, very important, because if you're looking at altogether a new problem where you don't have any idea how to formulate it from scratch, it becomes extremely critical that you know what are the key aspects of the problem that you're looking at and what is the simplest way to get to the answer. You don't have to use the biggest and most complicated tool available, because in that one you also lose insight into the physics of the problem. So I'm giving you this particular example that we have developed a model, and we have to make sure that the model captures the physics and also model is implemented correctly. So what I have just mentioned here, that the viscous model that we have for the actuator disk model for the circular cylinder or actuator cylinder model, the power is 13% higher than the inviscid case. So the viscous effects or the turbulent flow effects are important. One can improve on this also, but it will be of the order. So clearly that we can, and the viscous effect that I will take into account is certainly important. But suppose you neglected the viscous effect and you kept the inviscid model, then still you will be within 13%. Okay, and also it turns out that m is equal to 10 is the one that is most important. So now and it also turns out, which was a very important actually observation that we had, and which became very controversial after we published this particular work, and there was a lot of debate, because the Betz limit of 59% that I showed you for a horizontal axis turbine, it turns out that it doesn't hold for a vertical axis turbine. And so a lot of people were kind of amazed that, so what is the limit for a vertical axis wind turbine? What is the equivalent limit to the Betz limit? Betz limit has been around since 1950s or 1945. And so that issue is not yet resolved. So we have our numbers, but I think we have to do some more investigation before we completely have a confidence of what these numbers are for a vertical axis wind turbine. So if you explore the problems in this fashion, then you can see that two things can happen. One is that, of course, we are in the business of also publishing and training the students so that they can get master's thesis or PhD thesis. So then these are the things that are newer in terms of what you discover. And so you don't know a priori that what you will discover, but the formulation of the problem and the tools that you are applying and what is the outcome, they're all very critical. And eventually, if you understand them, you can help the industry in implementation of these ideas. So now I'm going to consider the geometry of 2 watts, that is the interaction. And that application is important from the wind farm point of view, that how much they should be spacing among the two vertical axis turbines. And of course, that is important, because if there is a big wake here and big wake here for a certain amount of a certain velocity, say average velocity that you encounter in that particular part of the world, then these should, what is the effect if these two wakes of this one and this one interact with each other, what is going to be the overall effect. So that is an important factor to investigate. So that is what we do here. And suppose we are having a wind farm with alternative locations, then we are also studying this second configurations in which we have a third vertical axis wind turbine behind the first two in the front. So these kind of solutions can tell you that what is the best wind layout for the wind turbine, which can help you in terms of extracting maximum energy, but occupying the least amount of space. So again, you can see that the effect of the wake is shown here, and you can see that the wake is not interacting, but if you are more closer, then the wake will start interacting. So is it good or is it bad? This is what we need to know. So what you see here, that the spacing between the two turbines is, now what happens is this is spacing. So the spacing can be small, and then what happens if the spacing is larger? So one is clear that if the spacing is smaller, then you get harness more power, and as the spacing keeps on increasing, then you will have less power. And part of the reason is that as the spacing increases beyond a certain point, let us say in this particular example of 5 meters, then it turns out that both the turbines behave as if they are totally independent. There is no interaction at all. So in that context, I think this becomes important. So now again, we have tried to evaluate the effect of m equal to 5 and m equal to 10, m equal to 20 in our initial model. And so you can again see very interestingly that if your m is equal to 5, the maximum power is about 940. And if your m is equal to 10, then maximum power is about 1025. And if m is equal to 20 is about 1040. So m is equal to 10 or m equal to 20, and as I postulated before, it is a good number for our model. And so again, you can see the effect of the wake and interaction if you have a larger spacing versus smaller spacing. So I'm showing you some of the charts, but you can generate a tremendous amount of data from the computer, and then you can analyze the data as appears to be most useful. So now I'm showing you again some numbers here of the power and what is the change in power. So it turns out the change in power is largest, that is 6%, if the turbines are close to each other. And so similarly, you can show some other results here, which again tend to show the effect of the spacing. And so the effect of the spacing, particularly now we are having 3 turbines. So now you have wake here, and you have a wake here and wake here. And so the way the color is coded, we wanted to show the prominence of this particular wake. And so in this particular case, for a horizontal axis wind turbine, it turns out the layout is consistent and is going to be proper. So now what we have learned is that we can again optimize it, and there are various other ways to optimize it. We have a genetical algorithm, and we have other kind of algorithms for optimization that are available. So you can take the user completely out of it. And so we normally use the genetic algorithm, and we combine it to optimize the distance. But you can have a multi-objective genetic algorithm, and I think many of you in India use NCGA, that was developed by Professor Deb at the IIT Kanpur, and this is one of the very good multi-objective genetic algorithm, and is available free. So now, so we can again increase the power, by pairing the watts, and now we also know how do we do a layout for a wind farm, which is going to be optimal in terms of the generation of power and less use of land. So now I'm going to show you 2 applications, and these are all related to the vertical axis wind turbine. We are not going to talk about the horizontal axis wind turbine. That is a subject in itself, and I'm just focusing on this. So one of the things that is happening now, that people are using these small turbines, which are the vertical axis turbine of the Savonius type that I showed you, and you can put it at the intersection of the highway. So this is a freeway or a highway, and there's 2 lanes on this side, 2 lanes on that side. And this is an example actually in Turkey. So in Turkey, in some places, they have, this picture is actually from basically from the location in Turkey. And so what they have is that they have installed these turbines, and which are vertical axis turbines, and they don't really destroy the landscape either. They are not sore in the eye if you're driving. So the cars are going in this direction and this direction. And one of the advantage of these vertical axis wind turbine is that they are direction free. In a horizontal axis wind turbine, the direction is very important, and the direction of the wind is extremely critical. But in this case, whether the wind is coming in any direction, this way or this way, it doesn't really matter, because the turbine is going to operate the same way. So it turns out that they are really effective. And so the idea is that as the cars are going at 50 or 60 or 70 miles an hour, which is close to like 80 to 100 kilometers an hour, then how that velocity of the automobile can be harnessed, which is of course contains a tremendous amount of kinetic energy by these vertical axis turbines. And of course, you can optimize how much is the distance they should be placed at, and how do you, so that becomes that effect of interaction among the turbines. And also, you can also see what is the height and diameter. All these can be optimized to see what is the effect. So the idea is to harness the kinetic energy of the passing vehicles. Now again, we are going to use the tools of ANSYS Fluent or computational fluid dynamics or whatever you may have. And what you see here is this is what is called an unstructured grid, which means that you have these triangles or tetrahedra, and this is your vertical axis wind turbine, one of them, and here you have the car. So I want to keep it simple, although we have done calculations where you have an array, periodic array of vertical axis wind turbine that I showed you in the previous chart. And there is this car, which is, again, we have taken a simple model, and this is a good enough model. And so what we want to see is what happens if the car is passing. So at a large distance, there is no effect on this turbine, but as the car comes closer and closer, the wind that is generated by the car is going to rotate the turbine, and it is going to generate the energy. So that is the whole idea. And of course, you have to generate this mesh very carefully. As I told you, this is one of the building blocks of CFD. And those of you who have worked in this area, you are aware of how to do this. So now again, I'm showing you in this particular picture. As a matter of fact, this was a very nice video, which I found that on this computer that I'm using is not working, because I had generated this on another computer. And so I have several computers because I use them. I've been teaching actually online for the last 2 years because of COVID. And so as a result of that, I alternately work on one computer or the other, but this doesn't have a software to run the video. But anyway, it isn't really important. So you have a little vertical axis cylinder or watt, and then you have this car model, and these are the details of the car model. And this is a simplified car model, but this is one of the cars which is a sedan, and this is more like a Toyota Camry. And so we are again using the fan boundary condition and other things that I mentioned about the Navier-Stokes solution. But one thing now becomes more complicated. That so far I had talked about the study problem. Now it is an unstudied problem because the car is moving. So the solution methodology and the time it takes to get the solution becomes a lot longer and becomes a lot more, not complex, but you generate a tremendous amount of data, because now you are basically doing the solutions at a very, very small interval. And so the solution becomes important as the car approaches the cylinder. And of course, you can take an array of cylinders, and then it becomes a lot more complicated. But in order to keep it focused, I'm just going to show you this. So now you can see that this is a 50 miles per hour and 60 miles per hour. So what we are considering here is that once the car approaches the actuator cylinder, then we are going to assume that it is going to, in the range that we are interested in, it acquires the velocity of 50, 60, or 70 miles per hour, which are the usual speed on freeway in the United States. And you can convert it like, it will become close to about 75 to 100 kilometers per hour. And so what you see here is that first you create a steady state solution to make sure that it's correct. And then you are doing a solution here, which is unsteady solution. You can see the formation of these vortices and very complex fluid structure behind the car. And once you go further, then these vortices then they start mixing with the nearby flow. So as a result of that, you can see that as the car is moving from here, where the flow is almost steady, and going towards the cylinder, the flow becomes more, it leaves a huge wake. And this wake of the car is the one that creates a fluctuating wind velocity, and that wind velocity then interacts with the vertical axis turbine. And so now you can see here the power that is generated. And so what is the effect of the power at 50, 60, and 70 miles per hour? And so this is the location, which is, you can see, is the one that is where the actuator cylinder is. And that is where the power generated is maximum. And as the car moves away from there, the power becomes almost, flat. But it's still going from, say, 0 meters, which is the location of the actuator cylinder, going only a 50-meter distance away. It goes from 300 maximum to about 150 or 100 or 200, depending if it is higher velocity of the car, 70 miles per hour, and then of course it goes to 200. There's a lower velocity, then it goes to about 150 or 140. So it is quite clear that, and if you come here, which is on the negative part of the axis, then the power generated is the steady power which is generated by the car. So you can see that you can really harness larger power by having this actuator cylinder. Now it turns out that, which results I'm not showing you here, that if you have an area of cylinder, then this power increases by a factor of 3. So that you can generate a really significant amount of power. And I showed you in isolated 2 turbine case and 3 turbine case. So in this case, in the array, you have 2, 3, 4 turbines. And so how far closer they are, it makes matter. So you can do all that study and show that you can generate a significant amount of power with that. So it turns out in Turkey, where this has been installed, they are using this power and from the turbine. Of course, the one thing is more positive in this case is that the cars are going all the time, and so the car are moving on the freeway 24 hours, 7 days a week. So as a result of that, you don't have that particular situation that suddenly the wind has stopped. So if you have a vertical axis wind turbine, say in a land area or even offshore here, of course, the wind velocity is always available and higher. It turns out that the wind is always available because you have a moving car. So as a result of that, it is almost that the energy is always available in this watt. And so they can then use it for the street lighting or whatever purpose they need. And it turns out that it has been effective. Of course, not that many other countries have duplicated it, or it has become a popular way to use on the freeway. I mean, we have probably the largest freeway system in the world in the United States. But there is no excitement here to use this kind of technology to put on our freeways, because the problem is, again, is driven by the economics. The idea here is that if economics was not a problem, we could easily move from the fossil fuel energy to the renewable energy in a shorter period of time if money was not a problem. And of course, the transition, the money is a very important problem. And also you don't want to have any economic disruptions. So if it turns out that for 1 miles of highway to generate certain amount of energy, it turns out that you have to invest certain amount of money, is there a benefit? And which means that the people who are going to invest in that is primarily going to be the local transportation, state transportation agency, or maybe in some cases the federal transportation agency. Do they see benefit in CO2 mitigation by this kind of a technology? Probably not. And as a result of that, it is unlikely that many countries are going to have it. But nevertheless, it is important from our point of view in academia, and also some people may be interested in research, that we create this kind of problems for the students and tell them that these kind of possibilities exist. And even though they don't see the light of the day, this technology can be patented. And maybe it will never make any money, but even to create all this kind of a knowledge, a lot of tools have gone into creating these kind of ideas and solutions that I am presenting here. So now it is again showing the average increase in power related to the steady flow conditions, and the other one related to time. And this is more important actually, that you can see that how much, is the change in power and time. And I already told you, and these numbers, if you're interested, in going into depth, they may mean something, but otherwise, the most important thing is that you can have about 50 to 60% increase at a higher speed, and with the distance being only 1 meter between the two watts or two vertical axis turbines. So which is of course expected, but here you are simply quantifying it, that it is significant amount that you can generate. So instead of going into conclusion, I think the conclusions are quite self-evident, that's why I have just mentioned. So the other topic, which is also a research topic that I am going to mention is, and this is again based on the work of my students, and here we have a patent, and but of course, again, we are not able to exploit it, although we have made a small model to get the patent. And again, there are limitations of this technology also in terms of getting it, commercialized at a larger scale, but it has been commercialized by some people. And this is a picture that is a company called Sky Wind Power, and this is their concept that they have patented. And again, we are trying to harness this particular idea that power is proportional to the cubic of the velocity, or the wind velocity. So as I mentioned that on ground, the wind velocity, the first slide I showed you, is normally, class 1, class 2, class 3 wind in a large part of the world. And so it is about, say, 5 meters per second to 7 meters per second. There are few places the wind velocity is 10 meters per second. And so if you want to further harness the wind based on this particular equation that power is proportional to UQ, then it turns out that you have to go to a higher elevation. And so which means that you have to go a little bit above the ground. And how much above the ground? You can go maybe 500 meters, which is a very high, much higher level of ground, and you can get a wind speed of about anywhere 30 to 50 meters per second. And there's the wind at that altitude is not always very quiet, even under the quieter conditions. So, and of course, offshore also the wind is always blowing, and there also you can get the wind velocities of the order of 10 to 15 meters per second. But this is a concept which is called the airborne wind turbine concept. And so that is what we were looking at, that can we apply the tools that we have, and again, train the students in this particular research area. And so here is the concept that we have, and that is that we have this wind turbine, and which is a basically vertical axis wind turbine, and these are the forces that will act on it. So this is the free body diagram of an airborne watt. So now it turns out that these circular cylinders that we have, which are the vertical axis wind turbine, you can install them on a small drone, and you can have them in a small size because their height can be small and their diameter can be small. But the horizontal axis wind turbine, you cannot install on a drone. And the drone technology has become very popular, and also it has become very cheap compared to what it used to be, say, 10 years ago. So it turns out that that is the idea behind that we have. And of course, you can apply the physical principle based on this free body diagram, and that is the Newton's second law, the conservation of momentum and conservation. And so you can calculate. I will not go into these details. And the power law is the one which basically tells you that what will be the velocity at a certain height. So as I told you, the z is the height above the ground, and then you can calculate that what is the expected value based on a large amount of data that people have come up with this formula. And then so you can say the z should be, say, let us say 50 meters, 100 meters, in order to see that how far you want to go. Now, the concept that I showed you from the Skywind, they use a tethered wind turbine, just like a kite. And that is one of the ways. But we are talking about, in this particular presentation that my students have done, is what is called is a drone. And so now this is the ideal power that you can calculate, which is the thrust times the velocity. And so you can use the conservation of momentum to get this u2 comma 3, which are again the actuator model, and this is the height. So you can use all these simple relations. And then again, as I told you, that we are going to use whatever we have learned for a 2 watts together and 3 watts together. And so on a drone, we are only going to put either 2 watts or 3 watts, and we can certainly put 4, but you cannot put 20 of them, because the drone has some small size, and you cannot have a huge drone also because it costs money to fly a drone. So here we are going to assume that the velocity of 30 meters to 50 meters a second can be obtained at a 500 meter altitude from the formula that I showed you. And again, the technology that I showed you before for a 2 or 3 watts is going to be used. And so now we are using the number of blades is equal to 3 as actually inside the watt, and the chord length of each blade. So this is going a little bit in micro, because we had to go a little more detail in order to patent this technology, which I did not cover actually in the previous slides that I showed you. So here we have to really show that this is what you can manufacture and what you can do. And this is what we did in our lab. So we have number of blades, and the chord length of each blade is given. The aspect ratio is 4, which means that the length of the span versus the chord that is equal to 4. So that is what the aspect ratio is. Altitude is 500 meters. And the mass of the entire each of these watts or each of these turbines is anywhere from 14 to 21 kilo. And it turns out that in our actual patent, we had somewhere about 15 to 16 kilo. And the weight of the drone is about 40 kilo, depending on if you have only 2 or you have 3, then of course it can increase the weight. And so now you can see that we are showing the results, and with 2 and 3 watts, the system weight is in terms of the newtons is given by this. Newtons is nothing but the mass divided times the gravity. And so that is the unit of Newton, the kilogram meter per second square, and power required to climb. So this is very important, that the power to climb, that is the drone that you have, and which has its own weight, and it has these weight of the mounted vertical axis turbines, whether 2 or 3, it will require power to go to height of 500 meters. And so that power, if requires, is more than the power it will generate, then the whole experiment has failed, this is no good at all. So what you want to see is that the power that you require to take the drone 500 meters is less than the power that is generated by this vertical axis turbine that you have put on the drone. So then power required to hover is this, and you can measure it and you can calculate it. And the total power required is to climb and to hover. Because once you are at a height of 500 meters, then you have to hover there. You have to sit there for a while to generate the power. And then the other issue that will come up is how do you transmit that electrical power to the ground where it will be used. So there are a lot of actually technical issues. They may look trivial actually, but they are really very, very complex. So the total power required here is 10,000, 13,000, depending on whether you have 2 or 3 vertical axis turbines. And of course, again, we are going to 30 meters, 40 meters, 50 meters per second of wind. So we can again use the tools that we have developed. We can see how much is the power generated by 2 or 3 watts and at these speeds. And of course, if you have 50 meters per second speed, let us say at 500 meters per second height, then power generated is substantially more, is about 90,500 watts. And the total output is also substantial, is about 89. So it is also very interesting to see that if the speed is only 30 meters per second, don't go there, because the total output is going to be negative. So what we are saying is the power generated is this, but there is an amount of power that is required to take this drone at a certain height. And if that power is higher, then you are actually generating a negative total output. And that means that your whole project has failed. So if you are here and here, you are generating a positive power, and that is very important. So all these calculations you can do, and then you can have a laboratory scale experiment, and then you can demonstrate it, then you can have a patent, and maybe some company may become interested. But it might be useful for a localized area that you need these drones, and they are not very expensive actually. It turns out that you can generate this whole thing that I'm showing you the results. The total cost, particularly because the students were involved, we are not counting here the labor cost. So the total cost was basically that of the equipment, and it was about $3,000, which you can multiply by 75 to see how many rupees it is. And maybe, but if you add the labor, then of course it will go up. And this is for 3 watts. Again, you can see that 30 meters per second is moving. So you have to go to a higher speed, and then you can see that if you have 3 vertical axis turbine, which is of course the right results, you will get about 18,000. So now there are issues, which are of course mechanical issues. And so it turns out that we did this study that if the 2 watts, which are only say 2 on a drone, then if they are counter rotating, it is better than they are co-rotating. And there are physical reasons for that. But if you have 3 of them, and so that they are rotating in the directions that I'm showing you, or whatever directions they may be rotating, it turns out there is a moment that results. And moment means that there is a force on a sideways that will result. So then it becomes a mechanical problem of installation. So should we go from 2 to 4, or is there a way to handle the 3 watts? So what I am talking about is again that a very simple problem looks on the face of it actually is a very complex problem. It is as complex as designing the wing of an aeroplane, which I'm telling you with my own experience that these wind turbines, we always took it as very, very simple machines, but if you look at in the physics and modeling and in terms of the experimentation and making them work for the actual situation economically, all kind of technologies goes into it. And what you do here is that the tools that you are using are computer based. So you are generating a very large amount of data, but you can have experimental data also, which is available in the weather service if you like to. So I think I have already, basically summarized what I wanted to do or say about this particular section of the presentation. So now I just want to mention that the wind farm, how do you create a wind farm, is a very important area, because all the technology that I have shown you, you are not going to have a one isolated wind turbine sitting somewhere so that people can come and they can go and look at it and just as a kind of a tourist attraction. So you really want to either put on the shore or you want to put inside the land mass, or maybe some other creative solutions that I've shown you that you might even like to use it for drone. Of course, for the drone, you are not going to put in any kind of a horizontal axis turbine, doesn't make sense. So it turns out that there is a way that you have to deal with it. And there again, there's a lot of technological thing that goes in, which I am going to mention. But also I want to mention about that it turns out that the offshore wind turbine, they have a lot more pluses, and in contrast to the onshore or inland wind turbines. And so I will mention to you what they are. So there are environmental issues, there are public issues that are there, and because they are noisy and they can also, create some kind of difficulty with, say, flying creatures. And so people who are living in that neighborhood, they don't like that buzzing sound at all. And so they cannot be put inside the land. They have to be put in places which are quite far away. But onshore, sometimes, they are not, so in the eye, then I think they can be more effective. Or you can just go inside the ocean, and of course, the installations are much more expensive, but the wind speeds are higher, and nobody is going to object that. So now, for example, in the United States, in the state of Delaware or many other places, people are putting these offshore wind turbines. And in Denmark, of course, it's very common that if you go to Denmark, then you will find that near the sea, North Sea, they are putting in these turbines, and they really look pretty. Actually, they don't look that bad. And of course, the construction cost, etc., is higher, as I mentioned to you. And so all these economic factors also have to be taken into account. So now one of the problems which is there, and which is a huge problem, that in a case of wind farm, and as you can see that a wind turbine leave horizontal axis turbine, and the reason is they are huge in size. So you are talking about a size of the order of, say, 100 meters. And so they need very high towers, and of course the cost goes up. As a matter of fact, you have to create an elevator in order to do the maintenance, and by that elevator you have to go on the top to do the maintenance of the turbine, because the height of the tower itself can be 100 meters. And I have been to some of these installations, and I have seen that how complex it is. As a matter of fact, the length of these blades is so long that they have to be done in pieces, and then they have to be assembled to the place that they need it, because the place they are manufactured, how to carry them. So they are transported actually on the freight cars or freight railways, and then they are assembled in some place. So it is not a very simple technology. And now we are using, for example, composite materials. So these are huge wakes. And so if one turbine is sitting here, so there is an interaction among the wakes, of course, which I already alluded to in the context of the vertical axis turbine. And of course, if there is a turbine behind it, and it is behind the wake, it means that you are going to lose tremendous amount of power. So how do you deal with the wake? Now the intensity of these wakes become much more intense, bigger the size of the turbine. So it is more economical to have a big size turbine than a small size turbine. But including the cost of the tower and including the maintenance cost, the blade cost, and everything. But on the other hand, you want to have a central place from which you can generate a tremendous amount of power, and then you can feed into the transmission network so that it can serve as a power plant. so that wind farm can serve as a power plant for electricity power generation in that neighborhood of say 100,000 homes or whatever industry they want to feed into. Of course, there are other issues that have to be addressed, which I mentioned in the beginning, that wind power is intermittent and how do you store that? And the storing is not easy. Currently the cost of batteries is quite expensive, and other storage mechanism like flywheels or using some kind of pumps to pump the water at a higher elevation and use the potential energy of that water, they are completely not very practical solutions. And so the issue here that I'm showing you is that what do you do about creating a wind farm with this kind of a wake, with the large size turbines that everybody now has decided to use. So there is an idea that has come along in the last, I would say, 4 or 5 years. And one of my students has also worked on that idea. And there's it takes time to explain it, but in simple terms, it is called the wake steering. Wake steering means that if you can do something with it at a turbine level, that you can, instead of wake going in this direction, just behind it, you can steer it in other direction. So just like steering a car, you can steer the wake at an angle. And so if you can steer all these wakes at an angle, then it may turn out that if this is not going over here, it's going over some other angle, then you are put in, let us say, another turbine. And so you can then have a layout of a farm by wake steering, which is going to be much more efficient than the current scenario that we have. Even if we basically design in a fashion that we do the alternate ways and we can use some kind of optimization technique, but it turns out that none of them is satisfactory in terms of really harnessing the potential. And of course, one of the solutions is that you put them far, far away. And so if you put them far, far away, so there is no wake interaction. And so then you put in a turbine here and there is no wake coming to the turbine here. That is a good solution. I mean, you don't have to even think about it. But the problem is that it will require a large amount of land. So what we are trying from economics point of view is to minimize the amount of land required, but extract the maximum amount of energy. And in that case, the wake becomes a major problem. And so how do you analyze the wake and how do you steer the wake is now a current hot topic in the area of wind energy. So what I'm saying is that wind energy, to my surprise, remain a very fertile area of research, and newer stuff that comes in all kind of technology areas, not only aerodynamics, but also the materials, the controls, and so on. So I think that this is very important part. Now, if you have a vertical axis turbine, then this is another picture. And it turns out that you don't have this problem of wake, and you can have that very, very close. And I showed you and demonstrated you from our simulations. And so it turns out, but the disadvantage here is that you cannot generate a very large amount of power. They are very cheap. You don't need a very high tower, which is very expensive, because these towers have to withstand the storm and all kind of conditions. And so this is a structural engineering problem. And then their interior has to be designed so that, the repair and service and maintenance can be there. So in case of horizontal axis wind turbine, this is much simpler. But on the other hand, the total amount of power that you generate is small. But other than that, it has a potential. So I think that if you have a small wind farm for a village of, say, in which there are 5,000 households, they provide a good solution because the land area required is smaller, and also they are not as noisy as the other ones, because the bigger the size, then the noise problem becomes bigger. But it's not that they are not noisy, but they are much, much less noisy. But on the other hand, they are not the solution for generating a large amount of power that is needed for our sustaining our way of life that we have, that is the generation of electricity, generation of power for the industrial use. And of course, we are not talking about the transportation at all. in this particular case. And so what are the topics on wind energy which we have worked on and which people are looking at, that how we can design the aerofoil of the blade, which we have decided now, and we have concluded that it should be a 3-bladed horizontal axis turbine. And so it turns out that there are now technological tools that you can do the blade optimization. And we do that for wing of an aircraft all the time. So we can just take that technology and transport it to wind energy. Now, aeroelasticity is very important, which is important for example, aeroplane. It is important for many other applications. Actually, it's important for what goes on inside our body also, because most of the tubes that we have inside our body, whether they are arteries or veins or urological system, or the respiratory system, all those tubes are elastic. So aeroelastic effects is very important. So that is something that people are still looking at. And again, the technology from aerospace is directly applicable, and the codes have been developed, but they are more complex because you are not taking into account the fluid structure interaction. Now, fluid is a simple one, just like in aerospace is air. We are not talking about any of these fancy fluids or like polymers and so on. So, but it's still, the physics is quite complex. And of course, we want quieter wind turbines because wherever they are, the noise, they basically generate the broadband noise, and which is a buzzing hiss kind of a noise. And the people are very much disturbed because whenever the wind turbine is in operation, which is maybe majority of the day, and particularly night, and people are sleeping, they are very much opposed to it and they want it. And so now also, there is a migration of birds and migration of, some other, flying creatures. And it turns out that almost, not a small number, whatever wind turbines that have been installed worldwide, millions of birds, come near the wind turbines and they just get killed. And so that is again not only environmental problem, but that is again a problem related with humane treatment of our surroundings and our animals and our birds. So that is another issue that I have not listed here. And then there are new technologies that are coming up, and for aerospace as well as many other applications, including the cars, which are called active flow control, and which means that there are ways that we can modify the flow over the wind turbines, just like we can modify the flow over a car or modify the flow over a aeroplane wing. And so now we have what is called the MEMS, so micro electromechanical system technology, which are actuators that can be installed, and they can then laminarize the flow from turbulent to laminar. And as a result of that, you can harness not only wind energy, but you can reduce the drag, for example, for aeroplane wing and also for a car. And in turn, if you use less, for example, energy, which in case of aeroplane or a car, then the emissions are going to be less also. But this is emission free anyway, the wind energy that we are talking about, but still we can use the technology that is available in aerospace application to make it more useful for harnessing higher power from the wind. But still it is going to be less than 59% of the available power due to the Betz limit. Then of course the control system technology now we have, and some very, very nice new ideas are coming in, and that can now protect these wind turbines. Previously, this was a big problem that if there is icing, and certainly, that adds a weight on the blades. And so how do you de-ice? It is the same problem on aeroplane. If you have to fly the aeroplane in the winter, you have to de-ice the aeroplane. But it's not easy to de-ice the wind turbine. Of course, you can use the same technology, but you can, and everything adds to the cost. And of course, if the storms are, like you have 100 miles per hour wind, or you are, there are tornado conditions, then, the wind turbine can be uprooted, or, the blades can shear off. So how do you address that? So there are, again, we are the people have proposed to use, because these turbines are not cheap. Each installation and each wind turbine can, of say 1 megawatt power, can be as expensive, depending on which country and which place you're talking about. It's close to $10 million or more. So it means that you can use the technology for de-icing, which we can build in these blades, which means basically putting in some coil that heat the blades and remove the ice. But protection under wind storm is still an area that is very difficult. And a wind storm can be, like if it is in, for example, in Saudi Arabia, it can be consisting of, a lot of sand, So all those things are not that trivial. And if you do the analysis of whatever I have talked about, including even 10% of sand, then you will find that you are dealing with multi-phase flow, and you can train another 10 PhD students in that particular area. And of course, intermittent energy storage remains a worldwide issue and worldwide problem as we are transitioning to electrical power, whether it is a car or it is aviation or, you name it, transportation, then you need a storage, energy storage. And the intermittent power, which is the case for solar power also, because the sun doesn't shine 24 hours a day, that becomes an issue. And so wind is the same thing. It doesn't flow 24 hours a day. So people are working at it. And I'm confident that in next years, we will not be talking about these topics, some of these topics, because there will be tremendous change and tremendous improvement in these technologies. And now, just mentioning, that everybody has a role to play. I mean, people who are electrical engineers, people who are computer engineers, people who are aerodynamicists or mechanical engineers, people who are manufacturing engineers, people who are materials engineers. Nowadays, all the products that are being developed, they have become so multidisciplinary that everybody can contribute to have the best economical and most optimized product for a particular need or particular societal need. So I think that there is a tremendous room. And now, all these buzzwords that we have, they will no longer be buzzwords, like, machine learning, deep learning, or ANN, or data, large data. They are just going to become practical, and they will demonstrate that they are useful in achieving these goals in a faster time. To give an example, in the first case, aerofoil blade optimization, you will not believe it, that it is about 15 years ago or maybe more, that one of my students did the aerofoil optimization, did very good work, and he used the ANN, using the genetic algorithm. And that is we used to call the artificial neural network. Now, in today's world, if I write the same paper, I will call it the optimization of aerofoil for a wind turbine using machine learning. And if I have too many layers of neural network, then I will say optimization using the deep learning. And if you bring in some kind of some idea or aspect that it is so automatized, then you can even add some wording about artificial intelligence. So they are all, ideas have been all around. I mean, it's not that they have just popped up, in the last few years, but they have taken a new thrust, new applications, and now, they are being called, under different names. And so like human machine interface. So all these new names that are coming in, all these ideas have been around as far as I have seen my, 18, 19 years in industry and more than 20 years in academia. But I have just given you some view about one of the areas. And as I said, that I had prepared this presentation without recognizing what is going to be the focus. But as I have spoken, I have given it a little bit, if you want to call it a spin, so that it meets with the theme of the conference. And again, I see that this has been a great conference. And again, I want to thank the organizers, and particularly Professor and Dean Shubhangi for inviting me to this conference and giving me the honor to open the conference. And I do want to mention that, working on a project, I hope it comes through in the area of biogas generation with her team. And if it comes through, then we will remain involved. But I'm not new actually to the Indian scene. As a matter of fact, just a month ago, I again gave the same kind of a keynote lecture on a conference. I think, I don't know, I mean, there was some university in Jaipur. And so I have been involved with the Indian technical establishment for a long time, actually, going back to, early 80s over the years. And it has been a privilege actually to work with a lot of scientists and a lot of people. And it used to be in person, but now it is online, and it has its pluses and minuses, just like anything else. But again, I want to thank everybody who is listening, who has listened to my talk patiently. And I have not kept track of the time, but I think it is certainly much over an hour. So I will conclude my talk here, and thank you very much for your attention.
Thank you so much, Agrawal sir. It is indeed a great talk, and in time also. So thank you, sir, for enlightening us with your zeal of knowledge on the challenges, opportunities for engineers in next generation technology use for energy harvesting in windmills and wind turbine technology. I assure you that many of us will definitely take the key points and start working on them. Also, we are extremely grateful that in spite of the time zone differences, you agreed and delivered this session according to our schedule. So before actual end of the session, I would now like to take few questions from the participants. Sir, we are having few questions. With respect to the onshore or offshore will be the beneficial in Indian context? That is the first question which has been asked in the chat box.
Yeah, so if you may recall that I showed the very first slide, and that is the wind energy potential in India. And so everything depends on the quality of the wind, if you want to call it. And that means that is the wind speed that is available. And so inland in India, it turns out that the wind speed that is available, even on the best days, you can call it, when the wind is relatively of higher speed, is of class 2 or 3, which means is of the order of about 6 to 7 meters per second, and which is quite low in order to fully exploit a wind turbine. Because a wind turbine, suppose, is from a horizontal axis wind turbine and is bought from Siemens or Vestas or GE, they are quite expensive. And so, and the rated power is, about 30, 30%, which means that it can harness only 30% of the actual wind energy. And that is because of the limitation from the Betz limit, because of the viscous effects and other effects. And so you can do a simple back of the envelope calculation that to get a payoff in terms of the energy generation, you can see how much the energy we are paying, for example, in India. So right now, let us say coal, how much energy is being paid? Because the general public, they don't want to pay more money for energy. And already, a lot of people have difficulty in paying the current cost of energy. So that is not really suitable, in my judgment, the inland. Now, onshore, there is relatively a higher offshore. That is, if you go inside the, say, land into the ocean, maybe not too far, maybe, let us say, few hundred meters or maybe 1,000 meters, depending on the continental shelf. I think that India may have a little better potential, but it's still, the record, the map shows, not only this map, but it is being updated, every year or every time, that we will never have on the Indian shoreline, whether in the Bay of Bengal or the Arabian Sea, more than, let us say 10 meters per second. But the offshore installation of the wind turbine is extremely expensive. It is right now, could be depending upon, many other issues, not only the material cost, but also the labor cost and maintenance cost, etc., included, I think is a factor of 3 or 4. So again, if you take the economics into account, it doesn't make sense at all. But again, when we are comparing this, if we are comparing that the energy from the coal, etc., is competitive, then of course everything makes sense. So I would say, to make a simple answer, that under the Indian condition, if you have to have a choice in terms of the economics, wind energy doesn't have as much of a good potential as the solar energy. I think the solar panels and solar energy has a tremendous amount of opportunity and potential in terms of the cost and installation, and in the long run, in terms of maintenance as well. So I think that is my view, but people may have an alternative view. But it doesn't mean that we should not do any research or any more exploration. Maybe things will change downstream.
Okay, sir. Thank you. And our next question is based on what are the limitations of vertical axis and what are the advancement needed?
Okay, the vertical axis turbine is the limitation is that you cannot have, one of them is the size limitation. Size limitation both in terms of the diameter and as well as in the height. And so the way, you cannot take a vertical axis turbine, which is even say 5 meters in height, which is huge. And let us say about, I'm just throwing in a number, 10 meters in diameter. You cannot take that vertical axis turbine and put on a tower. So if you put on a tower at 100 meters, then of course it is very uneconomical. Then use a horizontal axis turbine, which everybody is using. So the advantage of vertical axis turbine is that you can use in a localized conditions where you can have a wind farm, and where the effect you can have a cluster of these small wind turbines, and they are cheaper. As a matter of fact, you can make them of wood, and you can make them of material which is much cheaper. And I did not mention here because I didn't think that I should bring it up. So I have a patent on a turbine is called LOT. So like we have a turbine called HOT, horizontal axis. We have a turbine called WAT, which are most well known. And there is another turbine which is called LOT, L-A-W-T. And actually this is, there is a company in Boston in the United States, and the owner is actually George Sorovi. And actually he is the one who had come up with this idea. Then we did the study for him. And so, which is called a looping airfoil wind turbine. And the idea was there that it can be very, very cheap for villages, not only in India, but in Africa and all over the places. And we demonstrated that you can use wind and cut the blades in the form of a wind turbine blade. But the mechanism of rotation is that it forms like some kind of a belt. So it is looping. It's a looping belt which goes like a vertically and then comes, which goes on a slope and comes vertically and comes horizontally, so forms a triangle. And that can have a much cheaper way to do it. And that also can operate under the Indian wind conditions of like about 6 to 7 meters per second. But that also has a problem in the sense that you have to have at least a certain level of wind coming in to mount it. So I think that again, there are many potential new ideas that I think in terms of wind energy harnessing, which could be cheaper and also could be could be used under the Indian condition. I remember that several years ago, I went to Nirma University in Ahmedabad, which is a private university, a very good university with a lot of very talented people. And there was a person who was doing a project, in the area of wind energy, and he had some very interesting ideas. And I don't recall exactly what the ideas were, but they were related to the vertical axis wind turbine. But as I told you that vertical axis wind turbine have a potential, but not for large scale consumption. Like you would not like to use them, near New Delhi, for example, or some industrial area of Mumbai, or some other places, where there is a tremendous number of people who are clustered in buildings for working buildings and also home buildings, which require a large amount of electrical power. And also for industrial use, of course, the amount of power required is very huge. And so they can only be used, I think, in a very kind of centralized location in some villages or for some special small needs. But they cannot be very useful for a large scale electricity generation.
Thank you, sir. Our next question is based on which simulation tool can be used for mesh study. And one more question along with that, is there any constraint or condition for V infinity?
Well, the tool that I mentioned and is most widely available around the world and cheaply available, particularly to the people who work in academia. They have what is called ANSYS India, and I think it's headquartered in Bangalore. And I know that there are a number of other local simulation tools that have been developed. I don't recall their names, but I do recall that they are competitive. But ANSYS India has this tool which is available actually in many universities. Because as I said, I have visited so many universities, and everywhere I have gone, the MTech students and PhD students, they have been using this tool. So it is easily available, and every university can afford it for guiding research to MTech and PhD students. So it's not that expensive, and that I will recommend is the tool which is very user friendly. And if you want to modify that tool, you can write a small user-defined function that you can insert in it. And that is not really a tremendous amount of work. So I would say that is one of the tools. And of course, there are older generation of tools, which I think now are gone. Because as I said, the earlier times, 20 years ago when I used to visit, there was a older generation of tools that was being used in the automobile industry in Pune and other places. But the newer tools, which are available worldwide and under very cheap licenses, particularly in academia, I would say, and there are no such limitations. I mean, the kind of presentation I did, it was a viscous flow, Reynolds average, Navier-Stokes equation based tools, and these tools are not only have depth, but also they are very broad in terms of applications. So you can use it for aerospace, automobile, wind turbine, all kind of applications. They have the technology built into them. And many of them, the training that is required for a student with an undergraduate background is, I would say, not more than 100 hours. And this is based on my experience that within 100 hours means about 1 month. So if you spend 20 to 30 hours per week, then you can learn the basics of the tool. They have a lot of tutorials built into them. and you practice those tutorials, and they are so user friendly that once you know how to use them, and then practice is always useful. So practice more and more. Then the main thing is that you should have the ability to analyze the result from the tools. Where the mistake is done is that once you use the tool and you get any kind of result, and it could be total garbage, then you will not get the right answer. So you should be able to figure out that how to use the tool, which means that in case of CFD, the building blocks are the mesh generation, the geometry modeling, and the flow solver, and the turbulence model, and the boundary conditions, and then of course post-processing of the data. So if you know how to apply each building block of CFD properly, then you will get the right answer. But anywhere you make a mistake, you don't have a proper mesh, then the answer will be bad. So that is what is needed. But the tool itself has become quite user-friendly. It has not been developed in 1 year. I mean, it has been developed over a period of 20 plus years. And this ANSYS Fluent, over a period of time, it has become $1 billion corporation, not 1 billion, but several $1 billion corporation, and with this product being used all over the world, including India. So, and it is very much available in India, as I said. So I would say that tool at this stage doesn't have limitations, but any mathematical model or any mathematical tool has limitations. So there may be some problems that, it requires modifications, requires changes, but majority of the problems in the practical applications where fluid is flowing, whether internally or externally, these tools, if they are used properly, they are good enough and reasonably good enough for industrial applications.
Okay, thank you, sir. And we are having one more last question. We will take it and then we will just take a break. In case of heavy traffic in both the directions on the highway, the VAWT rotation direction will be clockwise or anti-clockwise, or it doesn't matter?
Yeah, I did make that statement actually. One of the advantage of a vertical axis wind turbine is it doesn't matter. And so whether it's moving clockwise or anti-clockwise doesn't make a difference.
Okay, okay. Thank you so much, sir.
As a matter of fact, the wind can be coming in any direction.
Okay, okay, okay. Thank you so much, sir. I would now like to just request you to please stop sharing. And could you please switch on your video so that...
Sir.
Hello?
Dr. Agarwal, sir. I am
Yes.
Shubhangi Ratkantiwar.
Yes.
Thank you so much, sir, for this excellent session and your valuable time shared with us. It must be very late, nearly about 2 a.m. in US.
It is 2 o'clock. And so I think that I will not attend the rest of the meeting. Actually, I need to now take off and maybe take some rest because tomorrow I have a very busy day. And so I need to now, maybe take a little bit of rest.
Yes,
I
sir, before
truly
leaving...
appreciate your efforts you have taken for us. Thank you so much, sir.
Thank
Okay,
you.
thank you.
Sir, before leaving, just could you please switch on the video if it is possible to take a group photograph?
So what should I do?
You can start video, sir.
Oh, okay. All right. Okay.
Yes, others, you are also requested to start your video so that we can have one group photograph. Peshattiwar, sir, I would request you to take the group picture. Ratkantiwar, ma'am, please switch on your video. Ratkantiwar, ma'am. Peshattiwar, sir, please proceed. Just a minute. Peshattiwar sir, have you taken? Atish sir,
Yes, ma'am. Yes, ma'am. 1 minute.
sir, please switch on your video also. Ashit Peshattiwar sir.
Yes, done, ma'am.
Okay, thank you, thank you. Okay. Peshattiwar sir, please share the PPT.
Okay, so I am going to sign off.
Sir, just a minute. A formal token of appreciation, please. Sorry for taking your time.
No
Just
problem.
one more minute. Yes.
No problem.
Thank you, Agarwal sir. I request you to accept a token of gratitude on behalf of organizing team and Yashwantrao Chavan College of Engineering, Nagpur, for sparing your valuable time and guiding us on the recent trends in the windmill energy harvesting area. Thank you, sir. Please accept this token.
Yeah, I'm very glad to accept this appreciation, and I really appreciate again, being a part of this particular faculty development program. And I wish that next six days are very fruitful to all the participants. And I see that there are about close to 170 participants. So I wish you all the best and great success.
Oh, thank you. Thank you so much again, sir. Dear participants, you must receive the feedback link, which is the attendance link also in the chat box. So you are requested to fill this current session attendance and feedback form for the accountability for the certification. We will share the link after every session, and please fill the form again. So as time constraint, participants, we are now moving towards our next session. The
So I'm
ideal
leaving now.
engineer. Yes, sir. Yes, sir. Yes.
Okay. All right. Thank you.
Okay. Thank you, sir. Thank you so much. The ideal engineer is composite. He is not a scientist. He is not a mathematician. He is not a sociologist or a writer, but he may use the knowledge and techniques of any or all of these disciplines in solving engineering problems. As Nathan Dougherty, American engineer, explained the definition of an engineer, preparing engineering graduates through innovative computer mediated learning technologies, pedagogies, lead to a good engineer. So as our next expert, I feel elated to introduce an educationalist, intellect, and an ace in engineering education, none other than Dr. Krishna Vedula from University of Massachusetts, Lowell, USA. We welcome you, sir.
Thank you.
Dr. Krishna Vedula is now based in India after 40 years as an engineering educator in US. He now devotes full time to IUCEE, Indo-Universal Collaboration for Engineering Education, a Section 8 company with headquarters in Hyderabad. The objective of IUCEE is to improve the quality and global relevance of engineering education in India with the assistance of a global network of industry and academic experts. During past 12 years, IUCEE has catalyzed significant transformations in engineering education in more than 100 institutions all over India. Dr. Vedula has completed his BTech from IIT Bombay in 1967. He did his MS from Drexel University in 1969 and completed his PhD from Michigan Tech University in 1980 in material science. He has over 40 years of academic teaching and research experience in material science and engineering, as well as in engineering administration at Case Western Reserve University, Hawaii State University, and University of Massachusetts Lowell in US. He has also spent 1 full year each at US National Science Foundation and the US Office of Naval Research, and 3 summers at NASA Lewis Research Center. Dr. Vedula was president International Federation of Engineering Education Societies, IFES, from 2010 to 2012. He has received numerous awards in recognition of his global leadership in engineering education, including the Nikola Tesla Chain Award at the 48th Conference on Engineering Pedagogy by International Society for Engineering Pedagogy, Thailand in 2019. He was awarded the title of International Engineering Educator Honors Scotia at WEEF, World Engineering Education Forum in 2014, Dubai. He received the 2014 IFES President Award as a Global Visionary at Dubai in 2009, and the Global Engineering and Engineering Technology Educator Award from the ASEE International Division, American Society for Engineering Education in 2009. Dr. Vedula is Chief Editor, Journal of Engineering Education Transformations, published in India since fall 2014, and has been co-chaired of 8 international conferences on transformations in engineering education, ICTIEE, since 2014 to 2021. These are all signature programs of IUCEE. Today, he will edify us with his vast educational engineering knowledge to focus on transforming engineering education to address the needs of a sustainable economy and society. I welcome you, sir, to this August gathering at YCC and request you to please proceed for the session. Over to you, sir.
Hey, thank you so much. That I did not recognize who you were introducing with all those things that you mentioned. So thank you so much. And I want to first actually, acknowledge already I've got the award at the end. The plaque that you sent me because I'm in Hyderabad, this was sent to me. So at the end of the session, I will show it again. So thank you very much.
Okay, sir.
Beautiful,
Thank
beautiful plaque for recognizing what I will be doing for the next 1.5 hours or so. Okay. I realize the participants must be quite exhausted already because of having been in the sessions already for the last 3 hours. And so, so thank you for your patience. As Dr. Ramesh Agarwal actually is a good friend of mine. I've known him for quite a bit, and I enjoyed listening to his conversations and presentation about wind energy, which actually is an important area. That part of what I will be emphasizing also. And so with that, let me try to share my screen. Okay, is my screen visible?
Yes, sir. It is visible.
Good. Okay, so I'll keep going. It's a very general kind of talk. It's not the high level technology that Professor Ramesh Agarwal talked about in specific area. Mine is more general, but I wanted to look at the title that was of the conference. And when I looked at the title, I saw the technological transitions and technological generations, okay, and then the challenges that you are facing. And if I look around, one of the things that really is a big transition is the need for the world to become more sustainable technologies. I think that is very important, and I'll spend some time explaining why that is important, and then I'll then spend some time on explaining how it is possible to do some research in those areas as well as educate our future generations, because they are the ones who will be bearing the brunt of these changes in the technologies in the future years. Okay, so so that fits right into the overall theme of the conference. I'm hope that I will do a reasonably good job of taking up this topic. And I noticed in the handout that Shubhangi has sent over that one of the main objective for the participants is to update multidisciplinary knowledge, give vent to ingenious ideas, and get involved in academic collaborations at national, international levels. And I think all of these are possible if you look at the overall field of sustainability. Okay, sustainable technology is sustainability, which I will explain in a little while. It is completely multidisciplinary. So whatever field you're in, you should be able to find a piece of the sustainability system and do some research in that area, and also get involved in projects, get your students involved, and also teach them about these concepts so that they are able to deal with the problems that we are facing due to the various things that we are doing to create problems in a sustainable environment. So the whole world is interested in this problem. Some of you might be familiar with Greta Thunberg, who a young lady, less than 20 years old, who recently made headlines with her concern for climate change and sustainability. And so it's a global problem and particularly important for us in India to address. And this is particularly important for research and education in India. So that's why I picked this topic. Oops, what happened to my sharing screen? I lost the screen. Sorry about that. I must have clicked on the stop sharing by mistake. Okay, so going on. So again, I underlined some of the concepts, multidisciplinary collaborations. All of these are possible with the topic that I'm talking about. So the sub theme within the talk that I talked about, focus will be on engineering education, how to transform engineering education, including teaching and research, to address the needs of sustainable economy and society. So I'm hoping this is something that will be of value to all of you. And the next 1 hour or so, I hope I can convince you that it's something that we all should take seriously and communicate that seriousness to our future generations. Dr. Ramesh Agarwal actually did emphasize one of these areas, which is of sustainability, which is renewable energy through wind energy. I will look at broader areas in general. Okay, so about the global warming, sometimes it's easy to say, okay, well, I don't know how important it is, but NASA and various reputed research agencies have clearly documented that there is global warming. Okay, it is not a myth. It's not a joke, but it's real. And the temperature of the globe has increased by 1.18 degrees centigrade since the 19th century. And the ocean itself has increased by 0.33 degrees centigrade since 1969 itself. Now, these are maybe small numbers, but they're very, very important in the context of the big picture because they can cause major changes in how in the world that we live in. It's like, say, if our body temperature normal is about 98.4 or 98.6, if that temperature changes significantly, we can get closer to death, right? So similarly, the world is at equilibrium at a certain temperature, and we are beginning to seeing these changes, and it's not good. Okay, so this results in decreasing snow cover throughout the world, shrinking ice sheets, and glaciers are receding, and all of this will, in a few years, in a few decades, some of us, I'm sure I won't live long enough to see the major impact of these changes, but your students will definitely start seeing these impacts, and I think it's up to us to help them have the background and the knowledge to deal with them. So sea level rise, many cities will disappear. They're declining Arctic CS, extreme events, floods. We're already seeing some of these in Chennai and other places. Floods are happening all over India. Then we have all these problems with the ocean becoming more acidified, and so there is scientific evidence for all these things. Okay, so and you're welcome to read some of these reports that will emphasize this. So this is not meant to scare you away, but it's the reality that we are facing that we need to think about. Okay, so that is the layout, and so if we go to the next slide, the reason for climate change. Okay, let me go a previous slide. Okay, let me ask you all, what is the most important reason for climate change? Why is all this happening? What's the chemistry behind it? What is the reason for that? Anybody want to jump in and give me a text message, chat message? Anybody think of what is the reason for it? Anybody think? Hopefully some of you are out there aware of what we're talking about. Let's see. Pollution. Okay, somebody says pollution. Thank you, Vipin. Any other comments? What's the chemistry behind the global warming? Why is the globe increasing in temperature? What's the chemistry? Okay, excess load on Mother Earth, less forest cover. Yeah, keep coming. Think about it. What's the chemistry? All of you are scientists and engineers. What is the chemistry behind? All of these are important. Okay, let's cover concrete jungle. All of these things are important, but what is the chemistry behind that these things are causing global warming? What is the chemistry behind it? What's the basic chemistry, fundamental science behind the all of these things that you mentioned? Forest cover, concrete jungle, advanced urbanization, Mother Earth. Somebody got it. Okay, carbon footprint. Okay, greenhouse gases. Okay, that's great. So this is what's important. Okay, that the carbon dioxide, which is produced by various means, is what is causing carbon footprint. That carbon footprint is increasing, and so if you look at the percentage of carbon dioxide, somebody has very carefully documented carbon dioxide as a function of years, all the way back to many years ago, and you can imagine the sophisticated level of research that has to be done to kind of figure out what was the carbon dioxide level over the years. But there's a sudden spike in 1950, around 1950, starting from about 1800, and that is it continues to increase. Okay, this spike in carbon dioxide level causes the Earth to get warmer. Why is that? Because carbon dioxide prevents the Earth from releasing the heat and getting to a normal temperature. So the heat accumulates because of the carbon dioxide, excess carbon dioxide in our atmosphere. Okay, so and what's important is that this is a result of human activity. Okay, the reason for carbon dioxide is because and as some of you pointed out, right, pollution, etc., etc. So human activity causes the carbon dioxide levels to increase, right? So can you give me one example in the chat box of a human activity that's causing carbon dioxide level to increase, in air to increase? Okay, give me somebody give me an example. Okay, already this. Okay, deforestation. Any other? Anybody else? What activity that we are involved with on a day-to-day basis is going to increase the carbon dioxide, carbon footprint? What are some of the activities that you can think of? Human activities. Okay, burning of fossil fuel. Okay, Nandini, good, excellent. Okay, exhaust in automobiles. Okay, what else? Traveling cars. Okay, excellent. Okay, so these are all excellent. Excessive use of energy, increased carbon dioxide emissions. Okay, fantastic. Okay, very good. So I can see that some of you are alert, and I'm glad to see that this is a lot of simple human activities causes carbon dioxide levels to increase. Okay, but we have to continue to do that, right? So I'm going to spend a few minutes now talking about the history of human activity. Okay, because that's important to understand, history of technology. And I would recommend that that I will go through this fairly fast. I would recommend though that in order to think about how to deal with the future, we need to know about the history. Okay, we need to think about the past. What did we do in the past? What did human beings do in the past? And so if you and you don't have to look at the details in this, but if you look at from 9000 BC all the way to 2000 AD, this is a plot of population. Okay, and population has increased enormously since about 1700, 1800. Okay, and then on this plot are all the important milestones in terms of technologies that have been developed, including beginning of metallurgy, and beginning of mathematics, invention of the automobile, the Watt engine, et cetera, et cetera. So this is, it's really interesting to look at history of technology. Okay, now if you think about the history of technology, some of you might have heard about the ages, different ages that we have come across, that we had over the years. Can anybody think of an age that's a part of history? Different ages. You might remember history book. Different ages that we have seen in the past years, many years. Anybody can think of that blank age? What are the types of ages that we've had? Anybody think of some adjective for the word age? History. Go back to your history and school, wherever. What kind of what age can you put in that blank space? Ancient age. Okay, that's good. But they're more specific. Evolution, human being. Okay, something related to materials. Ages related to materials, different materials. There you go. Absolutely. Somebody says Stone Age. Okay, what came after Stone Age? Okay, so we had we have had ages, and people in your history books, we have had the different ways that we have said. First is Stone Age, way back, just when no metals were available. Then we found that we could extract bronze from the stones that are lying around, and then later on, more recently, we found that we can extract iron. And that's when the Industrial Revolution started, and that's about the time when the population growth and the carbon dioxide emission and the carbon footprint started increasing enormously. And that's about the time when global warming started taking place because of the activities that we did. We had these huge monsters which are burning coal and producing iron and steel from iron ore, and so that's increasing the carbon footprint, carbon dioxide. We had coal mining, printing, machinery, and then we had locomotives, which emitted lots of carbon dioxide, and so the textiles and printing. And if you look at the locomotive, that really is where you have coal, the physics behind it. You have coal that is being burnt, and the heat is then used, is taking water, converting to steam, and the steam is then converted to mechanical energy through that piston. So this is the steam engine. Okay, the steam engine was really the basis for Industry 1.0. Okay, that Industrial Revolution started with this around that time. And so that's what's known as Industry 1.0 that we all talk about, right? We talk about 1.0, 2.0, 3.0, 4.0, which is what we are today in 4.0. So let's continue in our history. Again, people figured out that we can get crude oil from digging of the earth and natural gas. And so huge monsters, huge industries developed these things, and they required a lot of things and so as a result of the crude oil and the gasoline, we invented the 4-stroke internal combustion engine, and that led to the automobile. Okay, so we have lots and lots of cars using industrial combustion engine, using petroleum, and lots of other materials, lots of technologies around the car. Then aluminum production, started. Again, lots of activity in manufacturing, plastics production. All of these things started building up to after the Industrial Revolution started, and over the last couple of 100 years, all of these activities have been led to mass production, and then one of the important, very important parts of this, which is the Industry 2.0, is based on how we converted coal to steam, and using a turbine and a generator converted that to electric energy. Okay, that's the basis for 2.0, electric energy. 1.0 was just steam converted to mechanical energy, and then in this case now the coal and steam is converted electrical energy. So a huge impact of this, and you can notice that every step of this requires emission of carbon dioxide. So it's no surprise that global warming started with Industrial Revolution, human activity, and has kept on increasing over the last couple of 100 years. If you look at your energy consumption at home, okay, lots of things that you do at home. Every time you turn on a switch, you are burning coal. Okay, every time you use electricity, you're burning coal for the most part, because in India, 70% of our electricity production comes from coal. We have not yet made significant strides or changes to use renewable energy. So 70% of every time you turn on a light, the 70% of the energy that you're using is coming from coal, which is increasing the carbon, which is increasing carbon dioxide in the air, which is the carbon footprint of every time you turn on the light. So there's carbon footprint in everything that you do in your life, okay? And so the energy consumption as maps the population, as the population increases, we have a lot of energy, same parallelly, same energy consumption. It happens that in the developed countries, actually the energy consumption is even more. So there are more of culprits compared to the developed countries. In India, the per capita production of carbon dioxide is much less. So the developed countries are much more guilty of polluting the environment and causing the global warming compared to what we do in India. But still, being a large population, we produce a lot of carbon dioxide, and then of course, then after that, after Industry 2.0, we had communication became an important technology, and the various things went all the way. Now we have various ways of communicating, and now we have the various technologies used for that, and telephone, cell phone, TV, and then the Industry 3.0 is when internet came, and we had using internet in various ways to do various social and manufacturing activities. So that's Industry 3.0. We have the smartphone, amazing, complicated technology with many things in it. But again, each of these parts of the smartphone themselves, have a carbon footprint because the manufacturing process that is involved in producing those, and then of course now with the Internet of Things, where you have artificial intelligence, machine learning, robotics, automation, smart manufacturing, we are in the world of Industry 4.0, and so this is just a quick historical perspective of where we are, and so we have this challenge of carbon footprint and climate change and global warming, which we need to somehow deal with using some of these smart things that we're doing nowadays. Okay, so human activity results in global warming. Okay, we need to look at every human activity that we are doing and try to reduce its carbon footprint. And that's an important lesson that we need to communicate to the next generation. Okay, we have to convince ourselves and convince the next generation, because even if our generation goes away, the next generation will have to deal with the problem. They need to understand it. So if they continuously consume things and produce more and more carbon dioxide, there will be serious problems. Okay, so we need to include this as a significant part of our new technologies, develop and invent and do research on new technologies to reduce the carbon footprint, and do projects in those areas, and then teach our students through courses about these things and have them do projects and get them ready to take leadership roles in the future. Okay, so then next thing I want to talk about, I've talked a little bit about the sustainable economy and society to some extent, and I'll talk about how to transform engineering education, which is what I do for most of my time in India now, and for the last 10 years I've been trying to improve the quality of engineering education in about 100 engineering colleges all over India. Okay, so teaching and research for sustainable economy and society is very important, and each of you, okay, can do that. Okay, so look at every human activity and you can find something that's relevant, because everything is multidisciplinary, so that's relevant to your interest, background and field of expertise, and either build a research program in that area to develop technologies which will reduce the carbon footprint, or you might be wanting to do some projects and teach students in these interdisciplinary areas. And that is exactly very important, particularly from the national new education policy point of view, very important, right? So you can teach and do research by talking about designing and manufacturing to reduce the carbon footprint. So every designing and every manufacturing process that you talk about in your engineering discipline, you can look at it critically and say, how do I reduce the carbon footprint of this particular process that I'm teaching to my students? Okay, design for circular economy. Now, the term circular economy is very important, because there you're going to emphasize reuse, repair, remanufacture, recycle, the 4 Rs. And by focusing on these, we are reducing the carbon footprint by reducing consumption, reducing unnecessary production. And then renewable energy, waste and water and waste management, construction, huge construction and industry all over the country. We should find ways to reduce the carbon footprint that is resulting from all the materials that are used in cement production. Cement produces a lot of carbon dioxide, produces the production of cement, right? And many things like that. So everything that we do in construction, we have to look critically and say, how can we reduce the carbon footprint and its impact on the environment? Smart cities, smart manufacturing, smart everything can all be focused towards this concept. How do we reduce the carbon footprint and make our lives healthier and happier? Okay, so now the next question is, now that we have explained to you the challenge that we face in front of us, do you think our students will be able to be useful in this and to have useful lives in this environment by just mugging up and passing exams? Okay, the reason I emphasize that mugging and passing exams is, for the most part, our students in most of our classes, they just mug up and pass exams. They think that is the way to get an education, eventually get a job, right? If they just mug up and pass exams and get into the workforce, they are not going to be able to think critically and innovatively to come up with to do solutions to the problem that I just outlined. So that's important. Therefore, and the World Economic Forum has actually pointed out the skills that are needed for our futures and for our students, so that they should be able to deal with the new kinds of jobs, and many of them focusing on the sustainability issues will be important next 2-3 decades. And so critical thinking, analytical thinking, creativity, people management, emotional intelligence, being able to coordinate with others, project management, leadership, all of these are things that we hardly ever teach inside a course that we teach. Okay, we don't teach any of these things. These are important because if you have these skills, then you'll be able to look at things around you and find solutions to the problems around you. This is what industry is looking for. This is because that's called the future of job reports. When industry says our graduates are not employable or not employable, not ready to do jobs, it's because they lack these skills. Sometimes technical content also is a problem, but in addition to technical content, they need to have these skills, which is very important. And so communication itself is a very huge issue. We hardly ever emphasize the role of communication skills. Just speaking, talking, making presentations, working with others is very important. So whatever job people have, we have to teach our students to be better communicators. Okay, if you look at even if you look at the National Board of Accreditation, for example, NBA, and all of you are sometimes very busy with the NAC accreditation or NBA accreditation, and if you look at the outcomes that they expect from you when you submit your report, you have to show them that these are the attributes of the graduate that's coming out. Okay, now these attributes, look at the first 5. Only the first 5 have something to do with something that you can teach in a laboratory or in a classroom. The others, communication skills, teamwork, professionalism, impact on society, ethics, economics, project management, lifelong learning, these cannot be taught just simply by having the students sit in the classroom and listen to you. They can only be taught if they do projects. And if they do projects relevant to society and sustainability, then they actually move in the right direction in terms of solving some of these problems in the future. Okay, so think about areas within your own interest, within your own background, where you can actually have students work on projects relevant to sustainability concepts, and then have, while doing the projects, they will automatically develop these skills that NBA and NAC wants you to give to the students in the process. Okay, NEP again just recently came. Everybody's saying, how do I implement NEP? How do I implement NEP? This is it. Okay, it says we have to have a more holistic multidisciplinary education. What can be more holistic than addressing the problems of a sustainable society? All the types of things that I talked about, they're all holistic multidisciplinary topics. Okay, none of them says, okay, mechanical engineering, civil engineering, chemical, computer science. No, they're all multidisciplinary and holistic problems that not just involve technology, but involve society, sometimes politics, sometimes psychology, everything is involved, not just technical skills, multidisciplinary, holistic. So by doing a project, related to sustainability, and they can develop all these skills, right? And so it provides a learning environment for students. And what we need, that you all, okay, have to be motivated, energized, and capable. And I'm hoping that you will be move in that direction, or already are at that place, motivated, energized, capable, and that your administration is giving you the right environment and recognition for doing the kinds of things that are relevant to the future of the students and society. And so that is so what I'm talking about is relevant to your accreditation process. It's relevant to NAAC accreditation, NBA accreditation, relevant to NEP. It's also relevant to your institutional ranking, because a significant fraction of the institutional ranking depends on the teaching and learning process. And people have predicted that in the next 20 years, the last 20 years have been more of IT and startups related to IT. In the next 20 years, a lot of these startups and entrepreneurship will be in the area of sustainable technologies. So be aware of that, do some research in those areas, and encourage yourself and your students to do projects, come up with new ideas for ventures, for starting businesses. Ultimately, your students have to, more of them have to create jobs. You and your students have to create jobs, rather than just say, okay, 100 people go to Infosys, some people go to Wipro. We have to create jobs which will address the problems that society faces. Okay, so this is the focus on the next few slides will be on trying to convince you that learning engineering can only be done by doing engineering. Okay, you cannot just develop by just mugging up something and passing exam. You have to do engineering. So I'm going to get into some aspects of learning pedagogy. All of us are teachers, but we have never learned. I've never had a single course on how to teach. Okay, so I'm going to get into some aspects of things that we need to understand and about how to teach, so that the students become engineers who can address these large problems that society faces. Okay, so I'm going to spend a few slides on that. So what is doing engineering? Okay, doing engineering, let us see, let's go way back, go back in history, right? This guy is maybe thousands of years ago. Even today, of course, in some Adivasi areas, people are looking like that. But the original engineering of the bow and arrow, way back, right? The first people who invent, how did they, before physics, chemistry courses, engineering courses were ever developed, the engineer in this person, he looked around and says, okay, there is that rabbit, or there is that that animal that is running faster than me, and it looks like it might be good food to eat. So I'm hungry. So let me try to kill that animal, right? I can't kill it by just throwing a stone at it. So I have to invent a technology. So they looked around at nature and said, there is this particular stick that is flexible. And so so I found out about physics, elasticity. I bent it as a bow. If I bent it and put it back, it comes back. So maybe if I bend it, attach a string to it, the elastic energy can be stored in that bow. And then when I take an arrow and shoot it, that elastic energy gets released. And the arrow travels fast enough to nail and kill the animal that I'm trying to kill. So there is a lot of physics and chemistry involved in this whole process, because the materials that you're using is chemistry, the physics that you're using, elasticity, etc. And then I use my engineering mind, put it all together, and of course it did not happen immediately, right? I tried it a few times, I failed, tried it a few times again and failed. So engineering is about trial and error. You have to try some things and fail, and eventually you figure out that we can make it work. And so I'm hungry, I see an animal, maybe I can eat it, it's running fast, how can I catch it? And maybe I find a good stick, I tie a rope, bend it, tie a rope, etc. And so I've done engineering. I've engineered the bow and arrow, right? And today, of course, you go to the Olympics, you see the bows and arrows. The bows are much more sophisticated. Many sophisticated things are there, and so the technology has evolved over the years. Okay. And so now let us. I just want to take you on a time machine, take you on a little trip, okay, on a time machine, just for fun. This is a time machine, and I want to go through the time machine. Is one that you can go forward or backward in time by pressing a button. It's not been invented yet. Maybe some of you or your students might invent that, but the time machine is it's an interesting concept, right? So what I would do is have you think about some of the needs of human beings, because all technologies are based on human beings, right? Think of one technology, either for communication, health, or transportation that is used today. Okay, just think about it. Okay, and once you think about it, then then we go back 100 years. Okay, and 1922 on the time machine. You get out of your time machine and you look around you and see what technologies are being used for communication in 1922. You might want to text, okay? What's being used for communication in 1922 for health or transportation? Just put your thoughts in there. Let's see what anybody comes up with, okay? What technologies were being used in 1922, 100 years ago? Okay, let's have somebody give some answers. What technology were used for communication or any of those topics that I mentioned? Okay, communication, health, or transportation. Okay, anybody? Telephone? Well, horse and cart. Yes, of course, for transportation.
Sir,
Telephone?
hello,
Yeah.
excuse me, sir. Sir,
Yeah.
it is not in presentation mode.
What is not in? Oh,
PPT. Yes.
Oh, it's okay. That's fine. I'll get it back. I must have escaped it.
Yes.
Yeah.
Yes,
Okay.
yes, sir,
Yeah.
okay.
So telephone was not quite. I mean, it wasn't that common yet 100 years ago. Okay. So yeah. So others. Yeah, for health. What was being used? Transportation. Someone said horse and cart. Communication. Yeah. Telephone was not there. Before telephone, what was there? Okay, we just talking, sending letters, etc. Right? Health, yeah, simple, medicines, herbs, and so on, because none of the drugs and stuff were available. So if you look at that 1922, and then now you find your great grandmother in the village that you're at in 1922, and you put her on the time machine, right, and bring her with you, okay, and bring her to the present day, to 2022, and have her look at all the technology. Wow, look at this! I can take this little device, the cell phone, the mobile phone, and I can speak to my grandchildren 1,000 miles away. I can see their faces, or I can travel there within a day. Wow, look at all these technologies that and so these technologies were actually developed by engineers. Okay, that's why I keep telling students here that these are things that have been developed over the last 100 years. Amazing things developed by engineers, by being creative, by being innovative, and not just mugging up, but actually doing engineering and building these things. Okay, now let's go in time machine and go forward 100 years. Okay, and come up with some ideas as to what you will see being used as technologies for communication, health, or transportation in the year 2122. Okay, let's see. Take a wild guess. Okay, what you might see in the year 2122. Okay, just think about that. Okay, anybody have any? Let's at least get one or two reactions to that. What technologies do you think will be in 2122? Artificial intelligence for what? For what need? What will be the need that's addressing? Communication, health, transportation, space shuttles for transportation. Okay. What else? Others? Health, maybe. AI for health. Okay, maybe. Okay. Okay. So you can. It's difficult even to imagine. Okay, what might be happening, what might come, because your great grandmother in 1922 could not have imagined that something like a cell phone would be available today. So we cannot really imagine what would be available 100 years from now. But important thing is all of these would have been designed and developed by our students and their students. Okay, they will invent and develop these technologies. And so now if we get them ready, they should be able to do these things in a way that addresses the global challenges and create a circular economy. Okay, So engineers will invent and develop technologies, and then they will lead the change along with other citizens of the country, right? So engineers, so by doing engineering, not by mugging up and passing exams. So the message I'm hitting again and again here is that think about your own activities in your classroom, in your courses that you teach, and say how much of that, what fraction of that is really just mugging up and passing exams done by the students. If it's a large fraction, then you really have to make a significant change in how you teach so that they actually learn to do engineering rather than just mug up and pass engineering, okay? So how to teach students to do engineering, okay? Let's take the example of riding a bicycle. Okay, if I want to teach somebody to ride a bicycle, I can maybe give them books about bicycles to read, give them a lecture about with PowerPoint slides about bicycles, and give them a video of somebody riding a bicycle, or I can show them somebody riding a bicycle. But by doing any of these things, they're still not going to learn how to ride a bicycle. Yet, everything that we teach in engineering courses follow these 4 formats, okay? But the only way to teach them how to ride a bicycle is to go beyond, mugging up and passing exams. They have to learn to ride a bicycle by actually getting on the bicycle and falling down, getting on the bicycle, falling down. So engineering is a lot of trial and error and little guidance. So your job is really to help the students get on the bicycle and help them balance and help them learn how to ride a bicycle, and eventually they'll be able to do it themselves, right? So as mentors, so let them do engineering, let them work on projects, and while they're working on projects, they will make mistakes. Let them try something new again and again, and then help them, guide them to succeed in doing projects. So project-based learning by trial and error is the most important pedagogy for you to be able to teach students to do the right thing, to do engineering, and address the sustainability concepts that we talked about, right? Doing engineering, even from childhood in schools, we have to help them do engineering. Okay, this is how we teach. Most of the time, large classrooms sitting in front, writing on the board, right? Most of us, we teach like this. This is how we teach. How can we expect these students to become able to deal with the real world problems? They just because they'll end up just mugging up something, right? We have to change how we teach. That's one important message I want to give you. This is what I keep talking to faculty all over the world, not just in India, even in the United States, same problem. We have to change how we teach. And particularly nowadays with online, it becomes even more of a problem. This interactivity with each other is reduced and so on. And so we have to change how we teach. And so our classroom looks more like what's on top here, but we have to change it to a system where they have cooperative learning, project work, and interact and develop the kinds of skills that are needed to be real engineers who can solve problems. Okay, as I said, that's the only way to have the skills that the World Economic Forum wants us to do is by doing projects and not by mugging up and passing engineering. So I keep on emphasizing that. Now, this is an important cycle that I want, I'm sure many of you are familiar with in your courses. Some of you must be already using this. This is called the design process, informed design process. So when a team confronts a situation, they need to first define the problem. On almost all our courses, we just give them the problem and say, solve it. No, they have to be confronted with a real situation and let them clarify and define the problem. The next step is they have to do research, investigate the possible reasons for the problem and possible solutions to the problem. Then they have to see, okay, which of these solutions can I use to solve the problem? So alternate designs and be able to compare them. And so this develops the team skills, critical thinking, and innovative thinking. All of these are developed just by going through this design thinking process. And then finally, I have all these possible solutions. I have to decide as a team which is most viable. I justify the solution and I build a prototype. It may not work the first time, okay? So then I can go back and change the design or change the some of the criteria and build another prototype. And eventually it works and you have a working solution. So this design thinking process should be used. This is also same as problem-based learning, CDIO, many different names for this kind of approach. This is what we must have our students follow in every course starting from the first year. And there's a significant part of their growth as an engineer, of doing engineering. Okay, very, very important. Keep that in mind all the time. And this is what will allow our students to get the attributes that NBA wants us to give them. And so this is the Bloom's taxonomy that many of you are familiar with. Right now we are stuck. Most of our courses are stuck in the bottom. The students are only just memorizing. Maybe some of them are getting to the point of understanding. A few might get to apply, but very few are going to the higher levels of Bloom's taxonomy, which is analyze, evaluate, and create. That is when you actually do engineering. We must focus on getting to that level in as many of our courses as possible, because that's the only way to do engineering. So all of these concepts, this is how we learn how to teach better, by using this understanding. And most of us have never had a single course in how to teach. So we have no idea that there's something called Bloom's taxonomy. There's something called learning objectives. And so we learn it somehow on the job. But I think we need to have courses for faculty to understand these things. And that is what I do, my IUC does a lot of time. New education policy again, to get robust solutions and come up with all of these require us to go to that level of create in our education process for in the Bloom's taxonomy and to get to the new education policy. Okay, so we have a mantra. I'll just spend a few minutes now talking about IUC. Okay, talking about IUC and how we try to do some of the things that I talked about. I've talked about the the environment that we have to deal with, sustainability concepts and understand what is happening in society. We help our students understand the problems that society faces in terms of sustainability and the technologies that are needed to the renewable energy, water, global circular economy, manufacturing, smart manufacturing, all of these things. So then how to teach our students to learn all of these things and do projects in those areas, and also how to teach our students and ourselves how to do research in some of these areas so that they are actually advancing their knowledge, understanding of the topic. So we have a mantra: I am teaching, are they learning? Okay, and so if we have, and so what does learning involve? As I told you in the Bloom's taxonomy, learning involves first remembering, understanding, applying, evaluating, analyzing, and then creating the highest level. Okay, so we have to get our students to learn at these levels and go to the highest level possible. Okay, so I'm teaching, are they learning to create? Are they learning to analyze? Are they learning to evaluate? Not just mug up something and pass exams. So that's the question I need to ask myself all the time, and that is the IUC mantra. Okay, so this is Bloom's taxonomy that I showed you earlier. Okay, now the challenge is this becomes even more challenging. It's already a challenging, but it becomes more challenging when we have online classes where I can, just like where I'm with you, right? I can barely see you. I cannot get to to talk with you in small groups. I cannot get to interact with you. So this is a big disadvantage. And so we need to really have some definite face-to-face interactions as well. We cannot just completely go to online and expect somehow that students will start creating something, analyze, evaluate. We have to have more face-to-face interactions. Maybe a blended approach is what's critical. And so this is a challenge that we all have to figure out how to solve. Okay, once we teach them in a way that they remember or understand, apply, evaluate, analyze, and create, how do we assess? How do we know that they've learned how to create? How do we assess whether they've learned to analyze? How do we assess whether they've learned to evaluate? So that becomes a very important thing. And this has to be done through continuous assessment. Okay, continuous assessment and by reflection, but by having assessment every lecture, get some feedback. There's an interesting technique that I've used in my career is I call it the 1 minute paper, right? At the end of each lecture class that I taught, I gave just a one sheet of paper saying what was the concept that was most clear to you today in today's class. The second is what was the concept that was least clear to you in today's class, and I give it to them right at the end of the class, right? And I collect maybe 60 students. I collect that up, go back to my office, and I quickly glance through them, and I realized that there's some concepts that they did not understand and some concept they understood, and that allows me to next time go and re-emphasize or clarify some of the things that they had doubts about. And this continuous feedback allows me to improve the way I teach and do things that are interactive, create a dynamic classroom. I can reflect on what changes I'm making in the education process to get them to the point of creating or doing engineering. And then all of this is research. Okay, and I share with other people, other faculty, I share with others in publications. And so this field of engineering education research, some of you, might want to take it seriously. Maybe you already have. So in addition to domain research, some of you might be interested in doing engineering education research, where you look at these kinds of things. You reflect on changes that you're making while you're teaching and write papers, publish papers, and share with other people. And so the journals, we have a journal, IUC has a journal that does this. So keep all this in mind as we move forward. Okay, so to spend more time on the how to assess, and so this is what okay, so this this again is very, very challenging in the online environment. So that's something that we all have to face up to. Even though the world is going more and more towards online, we have to be careful that we retain a lot of this doing engineering by face-to-face interactions is very, very critical. You cannot do engineering just by sitting in front of a computer. You have to do engineering by actually doing engineering. And so we have to be very aware of that and move in that direction rather than just caught up all the time. Oh yeah, everything will be online. The students are not learning anything in that process. Okay, be careful that they learn. Okay, so going back to what IUC does, just to summarize a few things that we do in the next 10 minutes or so, and then I won't keep you much longer because I know it's lunchtime and so on, and we'll interact a little bit. And so I'm teaching other learning. That's the mantra, right? So our focus, our mission statement is to improve the quality and global relevance of engineering education in India. Okay, so we have this organization started way back about 15 years ago. So we focus on pedagogy and research, teaching methods, project-based learning, and we have webinars and workshops and all that. We started way back when Narayan Murthy of Infosys and Desh Deshpande, he gave us a little money to conduct workshops. Then we have a subscription model. We have several colleges that are now members of our consortium. Then we have faculty-focused programs, teacher certification, national conferences. We have leadership programs. We have a summit every year. Now we have chapters everywhere. Now our college is called student chapters. And after I came back 2 years ago, we formed a Section 8 company. And so now it's very well structured. And we have a board on the right-hand side, which is for the IUC Foundation India. We have a few people in the US that continue to run our programs over there. And so we work together in the common mission, improving the quality of engineering education in India with focus on project-based learning and topics related to sustainability. Okay, so we have faculty development programs, student programs, institutional development programs, global partnerships, various things, lots and lots of things. Uday Desai, who was the former director of IIT Hyderabad, is one of our advisors. Indira Parekh from Liberal Arts University, Manu Vora from Chicago. So we have a lot of people, global experts who help us in various ways. So in this student development, faculty development, leadership engagement, and we work on the help colleges on their priorities as they related to the teaching and learning process and sustainability. Okay, so we have a lot of industry friends who give us some donations and who help us out and who also provide partnerships for our colleges to participate in. And so we have 50 members that are consortium members, another 50 work with us. And here's some statistics about the lakhs of students that we're involved, that we have worked with the last 15 years. Okay, and those of you who are from colleges, different colleges that may not be a member of the consortium yet, this information available on our website, iuc.org, or you can email me, krishna@iuc.org. Okay, so our goal is to provide an ecosystem. Ecosystem means a range of different programs where the graduate can benefit from this, the teachers can benefit from these programs and become better engineers. We have a network of global experts from all over the world who participate in our programs through various activities for faculty development and student development, etc. Some of our consortium institutions are all the way from Chitkara University in the north down to Tyagaraja College of Engineering in Madurai, people from Telangana, Maharashtra, and so we focus on various aspects, particularly on project-based learning, so that the outcomes and the NBA outcomes from 6 to 12 can be easily shown, documented through project-based learning. Again, we focus on changing how we teach. I want to spend a couple of minutes on this particular certification program. Remember, I said most of us have never taken a course. I never took a course on how to teach before I started teaching. And that is true for most people. We might get a PhD and immediately somebody says, here's a course, here's a book, go and teach. Okay, that's how we are. But none of us has been taught, has taken a single course on how to teach. Just imagine if you have never learned how to drive, you get into a car and start driving, you're going to kill people, right? So you never learned how to teach, you're getting into a classroom and start teaching, you're killing the students, okay? So we have to learn how to teach. And this is our effort to help faculty through the certification program, which is recognized by a group in Austria. There were 6 modules in this, and the bottom you see pictures of the faculty from all over the world, led by Dr. Veena Kumaran, who had experience in IIT Delhi, knows the Indian condition very well. And this program is designed by all of these people from various parts of the world. 6 modules. 1 module on how to teach, teaching and learning, right? Principles. How do students learn? Okay, we have to understand how students learn before we can actually teach them, right? The principles of teaching and learning and how students get motivated. Second, how do you develop curriculum so that you're addressing the outcomes, not just making a list of topics? Third, how to create a dynamic classroom where you're interacting with the students regularly. Remember, the attention span of students drops rapidly. After first 10 minutes in a classroom, their attention span is gone. So if you continue to speak continuously monologue as a lecture, after 10 minutes, you can be sure that none of them is listening to what you're saying or paying attention. You're wasting your time after 10 minutes unless you get them engaged in some active activity during the classroom, talk to each other, work with each other. There's various techniques to do that. And that's the dynamic classroom we teach. Then how to use technology, then how to do collaborative learning and project-based learning. And finally, most importantly, how to assess the work done by them, whether it is remembering or understanding, applying, assessing at the higher levels is much more difficult. How do you assess whether the person is creating something? How do you assess a person whether they are they're evaluating something, right? So much more difficult. So how to set quizzes and exams to address all of these things. Okay, we have a very unique program with my friend from Purdue, Bill Oakes from Purdue University, EPICS program, Engineering Projects and Community Service. Okay, so if you look around in any community, urban or rural community near your college, you find so many problems that need to be solved. Many of them are related to sustainability concepts. Might have to do with the water, waste management, recycling, education. Because many of the schools, low-income schools, don't have proper facilities and education. So all of these we can connect with our engineering students, can develop small projects to work and help these communities. And that is a very important way by which they can develop the skills of creative thinking, innovative thinking, entrepreneurial thinking, understand the holistic and multidisciplinary nature of the world and of society and of engineering concepts. So we've worked with many institutions throughout the country, and this is very much like what you is a program in India, for example, that we are involved with, which is called the Unnat Bharat Abhiyan. Okay, where you go to rural areas and address some of the problems and do projects. And all of these projects, whatever the project might be, when you do these projects, you develop the skills which allow you to design and build. Design thinking is involved, and so you can then use the same experience in any other context. You might use it to design a space shuttle. Same principles. Design thinking is involved, whether you build a space shuttle or whether you go to a village and help them improve the quality of their water. The same design thinking process is involved in the working with a team, communicating with each other, coming up with different solutions, and doing research on the possible solutions and building prototypes. All of these are important. So this is another signature program. So the certification program and the EPICS program using design thinking signature program that we follow, which follow this informed design process. We have webinars every week. Every week there are 2 or 3 webinars by distinguished people from around the world, and then we have annual conferences where our faculty share, our students share, and then we have a leadership summit in July every year. This the last 2 years that were virtual. This year we are going to go back to face-to-face in Goa. And the leadership sits together and comes up with ideas as to how to strategize for the next year. And then we have annual events. We have student chapters in most of our institutions, and they work on projects, work together, learn how to work as teams and develop leadership skills. They meet once a year or twice a year on events that they want to work on, right? And we have a global network, people from all over the world. Since I've been around the US for 40 years, lots of contacts, and we connect with all of those people to bring the best that's available from these experts to the network of colleges that we work with. Okay, so we faculty share and collaborate. We have a journal where our faculty will publish and papers in engineering education research every quarter. It's a Scopus Index journal. So some of you are doing research relevant to this, please come and work with us. We have a sponsor. ABET is one of our quality sponsor, and the Dassault Systems, MathWorks, some of these names you might have heard. They're very actively involved in working with us, and we focus heavily on what's required for the national education policy. We have a lot of different courses. This year, we are actually piloting a program with the first year students at 15 institutions, by giving them some mini courses that are relevant to sustainability and holistic multidisciplinary education. Okay, so we have 6 courses, one artificial intelligence for all, entrepreneurial thinking, leadership and sustainability, clean green campus, social emotional learning, and design thinking for community projects. So we just are completing this. In fact, tomorrow we'll be completing these 6 courses, 8 webinars for 4 months. We've had them, and students have participated. Hundreds of students from all these colleges have participated in a pilot, and so that gives them a more holistic, multidisciplinary approach towards what they will be learning the next 4 years beyond this first year. So we have Bill Oakes from Purdue focusing on design thinking. We have Vemuri from California focusing on artificial intelligence for all. We have Pratibha, who's an education psychologist, teaches us about social emotional learning, entrepreneurial thinking. You don't have to become an entrepreneur. Just thinking like an entrepreneur will make you creative and productive. So Shalini and Ranji take this course on entrepreneurial thinking. Clean Green Campus, we have people who have backgrounds in energy and waste management and water who teach this course on Clean Green Campus. We have another one on sustainability and leadership from for Arizona State University in Chicago. The people that teach various concepts in these areas, and so I'm ready to close the presentation. So while we are so the focus of my talk has been on transforming engineering education. Okay, that's been, as you can see, very, very clear, transforming engineering education. So we are not just stuck with students mugging and passing exams, because that is not doing engineering. If our students only learn how to mug up and pass exams, they are never going to be able to address the needs of a sustainable economy and society. And I've explained to you by giving examples that sustainable economy and society is required. It's a need, because the world, through global warming and carbon dioxide emissions and the carbon footprint, every human activity, every time I turn on a switch in my home, I am generating carbon dioxide. This cannot be sustainable. We have to find a way to balance what we are creating, carbon dioxide, and balance it with something that's going to eliminate that carbon footprint. So this is called a zero carbon footprint. So we come to a society where the carbon footprint is zero carbon society, where if you produce carbon dioxide using one activity, you have to do something else to reduce the carbon dioxide. That is where some of you mentioned in your chat boxes, forestation, right? Putting more plants and trees, because trees will take carbon dioxide, reduce carbon dioxide and give out oxygen. So things like that. So there are ways that we have to teach our students by doing projects, using project-based learning, to doing engineering to address the needs of a sustainable economy and society. Okay, so I hope that I have taken you all through this process of thinking about this need for multidisciplinarity and holistic approach. So think back in your own discipline and try to build connections with other disciplines as they are relevant to sustainability concepts. And think of doing research. There is funding available in various organizations. So look around for those funding agencies. So don't just stuck in one narrow area of your discipline. Say, I'm going to spend my whole life in this one narrow area. That is not going to be good for the society as a whole. Okay, so think of how to become more multidisciplinary research, address real problems, do fundamental research and applied research for real problems, and get your students involved with some of these ingenious ideas that you'll come up with by doing research in the areas, and get involved with collaborating with other universities and get your students involved with in collaboration, global collaborations on solving the problems that the world faces. Okay, so these are the 21st century trends and challenges. I think I've hit upon some of the challenges that we face and how we have to transition to the next generation. That is my email ID, krishna@iuc.org, and I hope I've that time that you've spent with me has been quite useful for you. Okay, so I'm going to stop sharing and open it up for any discussions that you might want to have. I will also show my plaque that I already got ahead of time. So thank you for giving me that. Okay, so thank you, Shivangi, for inviting me and for sending this plaque over.
Thank you.
Shivangi said 2 to 1 hour, a little more than 1 hour, and may have some questions. And I'm sure everybody is hungry after this long morning. So I thought I'll keep it reasonably short. Okay, great.
Okay. Thank you, sir, for your wonderful and inspirational session. And I'm sure that the participants would definitely be happy to hear about the transformation required for an educator in these recent days to address the needs of sustainable economy and society. And they will more focus on do engineering using project-based learning. Sir, at this platform, we seek your permission to appreciate our team from YCC who has cleared all 4 stages of IUCEE student projects for problem-based learning, PPBL 2021, and were facilitated at the annual conference ICTIEE 2022 in your esteemed presence.
Sure.
Peshattivar sir, please share the team details.
Yeah,
the team members.
Okay, you have the details, right? I know there was a team. I forget who the team. Somebody has the details. Good, very good. Yeah.
Yes. They have cleared all 4 phases.
Oh, wonderful.
So the team members
are excellent. Yeah.
The team members are Suhanto Sarkar, Kiran Temburne, Shweta Farkase, with the mentor Dr. T.G. Panse from Department of Electronics Engineering, YCC.
Wonderful. So thank you for putting that for the attention. Great. Yeah, this is good. So I'm glad some benefits you're receiving. But what you have to keep in mind is IUCEE, is needs membership. The colleges to become members. So you have to convince your administration, your principal and your owners, Megays and all. In fact, 15 years ago, 12 years ago, when we had a visits of universities from India coming to the US when I was there, I think the Megays, Mr. and Mrs. Megay actually visited, was part of that team that came at that time and saw various colleges in the United States. So, the YCC was a member for 1 or 2 years in between of consortium institution. I would like you all to convince your administration that is worth the small fee that we charge to become consortium member, to see many, many more of such projects from your students, many, many more exciting things from your college as a result of interaction with IUC. So thank you.
Okay, thank you, sir. I would now like to take few questions from the participants, which we are having in the chat box. The question is how we can assess the students' performance in PBL.
Yeah, so that's not easy. Okay, that's why it's very easy to assess performance. When they mug up and just vomit it out, it's easy to assess it, right? Great. So you have to have a rubrics. Okay, when in the project-based learning, you have to say, okay, when you do this project, okay, I'm going to put 10% of the grade for how you define the project. Okay, another 10% is how you work as a team, another 10% of how often you meet and communicate with each other, another 10% for the report that you submit, and another 10% for the final prototype, and so on. So you have to have a rubrics to define all these things here, and it can be done, but it requires a lot of thinking and so a lot of time, much more time than if you were to just assess somebody just mugging up and passing exams. So developing a rubrics for each part of the design thinking process is important. Okay, and then using that rubric and communicating that to the students all the time, letting them know this is what we're going to evaluate you. We're going to evaluate you on the teamwork and evaluate you on how you define the problem. You're going to evaluate how you communicate with each other, and so that way you're covering all the outcomes that the NBA wants, in the assessment process itself.
Okay, thank
I
you,
hope
sir.
that
Our
answers the
next question, yes, next question is, can we broadly classify PBL as self-directed learning?
Not, I mean, no, it's not. I mean, it's not self-directed because you're being guided, okay, by a mentor, a guide on the side, okay. So the role of the teacher is no longer the sage on the stage. You get up on the stage and give a lecture for 1 hour and go away. That has to stop completely. It's absolutely waste of time. Okay, get up on the stand, get up in front of a classroom, and you keep talking yak for 60 minutes. You are wasting your time, wasting their time. After 10 minutes, maybe even after 5 minutes, the students are gone. This is human psychology. And even in my lecture, this 1 hour, 10 minutes, I think most of you are doing something else for most of the time. You're not really paying attention. Because online is even worse. Attention span disappears. Okay, you're tempted to do something else. Same thing happens in the classroom. So you have to, so you have to be a faculty member. You have to be a guide on the side. So you give a project or a problem to a team of students. Okay, and have them define it, etc., but you have to be there. If you just let them do it on their own, they're not mature enough to do it the right way. Some of them might be, some of them might not be, but your role is a guide on the side. So it's not really self-directed, but it is assisted with some mentoring, okay, by proper professionals.
Okay, sir, in line with this, I also have one question, that what can be the major phases to be focused when we are implementing PBL actually in the classroom? Means we may have the faculty role or we may have a student role. So are there some specific phases to be focused with these two entities in the implementation, actual implementation?
Yeah, sure. I mean, I think that a good guide would be the the design thinking cycle that I showed, which is also the CDIO cycle. So if you so the first step, which is very important, is defining the problem. Okay, so the faculty member should not say in great detail this is the problem. They should give a more general approach, general type of problem, and say now define the details of the problem. Leave it to the team, and so that is one stage. Okay, that stage, then they have to define the problem and submit the report to you as a team. Okay, once they define the problem, then you have them understand, research possible solutions. Then they have to submit that to you. That's second stage. There's about 5 possible solutions. This solution has this disadvantage, this has this disadvantage, this is disadvantage. And then they're doing this all as a team of 4 or 5 students. So they have to document which student has done what, which students have done this, how do they work as a team, how did the team work, were they able to benefit from everybody's contribution, were they having some difficulties adjusting to each other and working efficiently as a team. All of this has to be documented, mentored and graded. And then after that, then they have to pick one of the solutions. And that's not easy because some solutions have some advantages, disadvantages, so on. So pick an optimal solution. In the real world, there is no perfect solution. You pick an optimal solution, and so I'm going to try this out. And then the most important step is to build a prototype. Before you actually go into production, go into something big, build a prototype. That's very, very important. So that phase is very important. And that again is done as a team. And once the prototype is done, then you have to test it. Does it solve the problem? Okay. And then if it solves the problem, you continue further and make a robust product out of it. If it does not solve the problem, then you go back and build a different prototype. So these are the different stages that are involved in the teaching project-based learning. So and again, people should not get scared. Oh my God, I can't do this. Some projects can be done, can be small. Can be just 2 or 3 week projects. Some projects can be a whole semester. But I would encourage people to start thinking small and take a course that you're teaching and come up with a project maybe that can be done in 2 or 3 weeks and give it to groups of students and then follow this process of design thinking and then try it out and see your role in how to make it work and then gradually graduate to larger projects. But I think it'll be good to have lots of small projects and maybe 1 or 2 big projects during the 4 years that people are involved with. And many projects might involve different disciplines, so you might have to connect with faculty from other departments and try to get them involved in the process of evaluating and guiding the the students, because you may not know all the answers that the students ask, but they have to find the solution, find the answers. It's called lifelong learning. Okay, from the internet, now information available at the fingertip, right? So you have to just guide them to find the right information. You may not have all the information. Okay.
Okay. Thank you, sir. One more question was there. I think it has been asked in this only. That is the design thinking possible in PBL? So we have to follow those steps, right, in design thinking.
Yeah, right. But both
For
of
the
these are
PBL.
kind of similar, just different names.
Yes,
CD,
yes,
some people use
yes.
CDIO, conceive, design, implement, and operate, something like that. Yeah.
Yes. So thank you, sir. Thank you once again.
Thank you.
And I
Thank
request you to please accept this virtual token of gratitude on behalf of.
I have the real one. I have the real one.
Yes, sir. Both. Yes. Yes, sir. Thank you for sparing your valuable time and
Okay.
guiding us.
Thank you, everybody. And Jay-
Okay, thank you, sir. Ratkantiwar ma'am, please over to you for sum up. And sir, we will also have one small photograph, group
Sure,
photograph again.
of course. And I will do
Ratkantiwar
some.
ma'am, Azia.
Shubhangi, how are you? And when we have a photograph, I'll do a little exercise, fun exercise for everybody. Okay.
Okay,
I'll show you what it is. I do that all the time
Yes, sir.
with my students and fan meetings. Where's Shubhangi? Come on, Shubhangi, come in. Let me see your face. I remember once when I came to Nagpur to YCC
Yes.
almost 10 years ago. And I made a mistake in the date, and I came there one day before I was supposed to come. And everything was confusing. And somehow Shubhangi managed to manage, and then she and her husband took us out that one evening to this, I think, temple that was there.
Yes, Swaminarayan temple.
Swaminarayan, right? That's Swaminarayan. Yeah, right. Temple, right. I remember that. Okay, so you want everybody to turn on your videos?
Yes, please,
Come on up.
everybody turn on the
Okay,
videos so that we
while
can
you're
have a
waiting
group
for everybody-
photos with sir.
While you're waiting for everybody to get ready, I'm going to warm you up a little bit, okay? This is called laughter yoga. Okay, we're going to do laughter yoga, a few minutes of laughter yoga, okay? I do this all the time with my students and with the faculty in meetings like this, and even face-to-face meetings. There's a lot of research on laughter yoga that's very beneficial. Some of you already might be knowing about it, okay? Laughter yoga is about laughing artificially. I don't have to have a joke to laugh, okay? You can just laugh artificially. And when you do that, laugh loudly, and so that the air is coming from the bottom of your belly. And that is good for the lungs, good for the brain, good for everything, okay? So laughter yoga, do that about 15-20 minutes a day. It'll cheer you up for the rest of your day, okay? So you're just going to do 2 minutes of it. I'm going to show you 2 exercises, laughter yoga exercises. Okay, the first one goes like this. I will do it once, and then we'll all repeat it. We'll all do it together twice. Okay, very simple. Okay, it goes like this. Okay, ho ho ha ha ha, ho ho ha ha ha. Okay, loudly, as loud as you can. Everybody, twice. Okay, go. Let's go. Ho ho ha ha ha, ho ho ha ha ha. Come on, guys. Come on.
Sir, actually, the participants are not able to unmute
they can't
themselves.
mute them. Okay, anyway,
Yeah.
let me see you wave your hands at least. Okay. Ho ho! Everybody do it. Just so. Ho ho! Ha ha ha! Ho ho! Ha ha ha! Ho ho! Ha ha ha! Okay, just do it. All right. And then the second exercise is a simple one. We're just going to go. Very good, very good. Yay! Okay, like children get excited. Very good, yay! Everybody, let's see me do the action at least. Very good, yay! All right, I'm done.
Yes, thank you, sir.
Take a picture.
Yes. Take a Peshattiwar, sir, please take a picture.
Oh, everybody's smiling. It's good. I can actually show my this. There you go. Shubhangi is here. Hi, Shubhangi. Very good. Yay! Okay, now take the picture.
Is it done,
Shubhangi.
sir? Okay.
Yeah, all done.
Yes,
Okay.
done, sir. Done.
Thank you, sir.
Thank you, everybody, and Jai Ho.
Thank you, sir. Thank you so much. Dear participants, please fill the feedback form. The link is shared with you in the chat box. It is request from the organizing team to all the participants to fill the feedback form for each session through the link shared with you during the session only in the chat box. towards the accountability of the certification. Dear participants, now we will take a lunch break and we'll again join for the next session at 3:15 p.m.
Amuli, what about the group
Yes, ma'am.
photo?
आता झाला मॅम
झाला
तुम्ही
का?
जेव्हा
Okay.
ऑनला आल्या ना ऑनलाईन तेव्हाच झालं.
Okay.
The link for the next hello, dear participants, one more instruction to all. Please rename yourself as your first name and last name, because few participants have name as admin or other than their first name and last name. So I request you to please name yourself so that the attendance would not have any issue. So rename yourself.